YouTube recording is live. Hello, YouTube. So, we're gonna do an ADS exam. In this case, like in our year, the exams got split into implementation and analysis. So this is gonna be an analysis exam. It's an open book exam, so we've got the book here. We got the exam here, and I'm gonna write the answers in LaTeX because the exam is gonna be in white space. So you're gonna be able to do that as well. And I think we're gonna get started. So I'm gonna start the timer, and we'll see. Okay, so let's have a look. Can I zoom in a bit more? Which of the following statements about asymptotic algorithmic complexities is false? N is big gamma of 1. N is big gamma of n log n. 2 to the power n plus 10,000 is 2 to the power n. And log n is big O of n log n. Okay, realistically speaking, we can already see that C is true, because this is just 2 to the power 1000 times 2 to the power n, which is a constant times 2 to the power n, which is big O of log n. Let's see, big gamma is at least this, so therefore big N is a higher order of magnitude than 1, so this is also true.
Think you should make the PDF viewer a bit larger so we can see the whole question.
Yep, good point. There we go. So we're looking for the thing that's false. We know A is true. We know C is true.
If you look at it, it's either A or B.
Hmm?
If you look at it properly, it's either A or B.
I mean,
It can't be
okay,
both.
that's fair.
It's either A, B, C, or D.
Yeah, that's a good point. For the people struggling to remember this, I think there's actually a thing in here, like going down the list of all the different complexities in order.
Yeah, there
Yeah.
is.
So here you can see like it is constant, logarithmic, linear, n log n, quadratic, and then we have cubic and other polynomials. So the question is n higher than n log n? Well, we can see. N log n is the n log n function, linear is lower than that, so the answer is no. So I think the answer for 1 is B.
Also, by the way, that's omega, not gamma, for the
Fuck.
video.
I keep messing up the Greek letters. So big omega. What are they called again? We have big O, big omega, and big
theta.
theta. And theta is like exactly that.
In general VC channel, there's a picture to see this nicely, but yeah.
Oh yeah, a big ass cheat sheet. So this one. I might actually save this and have a look at it. But this is like all the.
On the top right, it shows the time complexities. Yeah. So there you could see this answer.
Yeah. Okay, this is useful. I usually use another one, but we can use this. Okay, so first question done. Which of the following statements about asymptotic algorithmic complexity is false? If the the ceiling of a function is big O of f of n, or in this case big O of itself, if the function itself is a positive non-decreasing function that's always greater than 1. What else do we have? If dn is big O of n, then this doesn't seem right. If dn is big O of f of n, then a times dn is big O of f of n for any constant a bigger than 0. I think this is wrong already, because this should be for a constant a is bigger than 0.
What?
Or am I?
No, it's for any, because the definition of OFN is with a constant. So you just change your original constant to be a times that constant, and it'll stay the same.
Yeah, okay. That's a good point. Okay. If Pn is a polynomial in n, that's a polynomial with like degree n, right? Or not? Or just a polynomial in with the function being n?
Not in degree.
Then the tightest upper bound for log of p of n is O of n log n. So we have a logarithmic function of a polynomial of degree n. Right?
This is false, right?
Let's imagine. So if we have
Because a
imagine if
polynomial
n
would
is
be like n to the third,
yeah,
and that would be more.
then when we have the log of n to the third. Yeah, I think that's like bigger than n log n.
Okay.
That is upper bound for the log of
Actually,
p of
never
n.
mind. Never
But
mind.
the log of p of n, if it's a polynomial, then the log of it will always be a constant.
Oh yeah.
So and log constant is
Oh
C,
yeah,
or
okay.
O1.
I thought I got confused. I thought polynomial and n meant like a number to the power n. But
No.
it just means n to the power a number. So it's the other way around.
Mm-hmm.
Okay. So then this is, I guess this is true then, yeah. Or the tightest upper bound for the log of n to the power constant. Well, no, indeed. So
No, yeah.
then this would be wrong, because then it would be just a constant times log n, right?
Well, it
Yeah,
would
I
just
think
be
so.
I don't even think it would be a constant times log n. I think it might even just be actually. Yeah, no, it will be a constant divided by log n.
Yeah.
Yeah.
So then this is wrong. So the tightest upper bound would be big O of log n. Because like while if they it's important to keep in mind is they ask for the tightest upper bound. So while the function log n has an is theoretically speaking big O of n log n, because it is n log n or faster. However, it's not the tightest upper bound, because the tightest upper bound would be big O of log n. Therefore,
Mhm.
2 is C. We know that one is wrong. I see it actually compiles right now. Yeah, not very well, but it compiles. Consider the Java interface uninterface below, which is an ADT, for one of the data structures defined in this course. Which of the following structures cannot be efficiently implemented by only reusing methods from the data structure? From this interface. Note that the data structure implements every method on an interface with a big O of 1 time complexity. So we can get the first, we can get the last, we can add something at the first, we can add something to the last, and we can remove the thing at the first.
I don't know. The first thing I noticed is that you can't remove last. So I guess a thing which would need to remove last would be difficult, since you would have to remove the entire thing and add the rest to another thing.
Yeah, because that, like they say here O1 explicitly, so I think like removing everything would be big O of n. So,
Yeah, but that's not efficient.
It's stuck.
Yeah, and they also like cannot be efficiently implemented. So what has?
Whatever need to remove last.
Yeah, so let's see.
Q,
Q
I
A
removes
guess.
stack
first,
is
or Q removes first.
a stack is only like adds first. It
Oh,
depends how
it's
you
not
orient
last,
the stack then,
remove
I guess.
last.
A stack uses remove first.
Yeah.
A queue uses remove last.
Well, it
I mean,
depends.
technically, stack
A stack
uses
can
remove
use
top.
add last, remove last, and add first, remove first. It just depends how you orient the stack.
True. But you could implement a queue by just saying, you can make a function add first and make it do add last and remove first. So a queue can be implemented.
Yeah,
I
queue can be
suppose.
implemented. A stack can be implemented. A priority queue has a remove min, right? That would not be able to be implemented properly because then you'd
Yes,
have to
it does.
remove first
Yeah.
everything. So I'm quite sure the answer for 3 is A.
And the last, the circular linked list, that's easy. It's just a normal list, but you can do remove
Are
first,
you
add
sure
last, the
about
cycle.
this?
Yeah.
I mean, the priority queue is based on heaps, and heaps remove first is basically remove mean
They're
because
always
mean is
first.
at the root, so it's always the first element.
Yeah, but
Yeah,
how
but
are you gonna?
they're always log n because they have to keep the structure after they
Yeah,
remove the
there is no
first.
there is no heapify in here. And you are not allowed to additional method no additional methods
No,
allowed.
but you don't need heapify to make it.
Yeah, you need to.
How are you
just
gonna order it if you can't?
You can just have an empty priority queue and add all the elements. It's not the most efficient way, but You don't need it.
Yeah, but
Keep it.
this
But
interface
it's
isn't
priority queue anyway because all operations are log n, but these ones are O1, so we
Yeah.
have to change them.
but you can't you can't use any additional methods or additional stuff. It's just if you have this interface, can you make
Yeah.
a priority queue out of this?
Yeah, you
Yeah.
can just add first instead of doing heapify on something.
Okay. Consider the most time-efficient algorithm that uses O1 space to calculate and print the sum of every pair of consecutive elements S with n elements. For example, if S is 1, 2, 3, 4, 5, the algorithm should print 3, 5, 7, and 9, corresponding to 1 plus 2, 2 plus 3, 3 plus 4, and 4 plus 5. The sequence can change in between, but its final state needs to be the same as it was before the calculations. What is the tightest worst-case time complexity of such an algorithm S? Implemented using either a fixed size array or a singly linked list without a tail reference. The list has the following ADT: add first, add last, remove first, first, and size. And this is like this is about a singly linked list. Note that the ADT does not allow direct access to its nodes. The methods remove first and first return the element directly. Okay, so first of all, using an array, it should realistically just be big O of n, because accessing an element of an array is just big O of 1, and you can just loop through the array and just say pick this one and the next one, this one and the next one, this one and the next one, which are all just O of 1. Okay, give me a sec. Pratt is asking to be unmuted. Yo, you're unmuted, man.
Thank you.
You were probably muted sometime because your mic was spamming or something, but it's good now, I think.
Thank you. It's been like too long.
Okay, so with the array, I'm pretty positive it is just big O of n, and now it's only figuring out with a singularly linked list if it will be big O of n squared. Let's see. I'm pretty sure you're not allowed to use any other auxiliary data structures, because otherwise the question would be pretty stupid. Oh wait, you
Well,
can add first and add
Should be
last.
ON as well, right?
I mean, if we are allowed to keep reference to the previous element, it should be ON because you started first, you keep it, you see the next, you print the sum, you move the previous one.
Yeah, I am pretty certain it would be big O of n, because you have like add first, add last, and remove first. So you can remove the first one, then look at then add that element to the end, then look at the first, add it to the one you just removed, and then repeat that.
Actually, oh no, it prints the sums. No, never mind. I thought
Yeah.
it would print the final sum because then it would be a lot easier.
No, that would be hella easy. I wish, but I'm pretty
Yeah.
sure it's just big O of n for both of them.
There's two correct answers.
Mhm.
There's two correct answers, both A and B.
But they ask for the tightest,
The tightest.
so it's only A.
Yeah.
Yeah, but the answers have both A and B. I mean, yeah, I guess that you can do an ON implementation.
You're already looking at the answers.
Yeah.
Let's not do that until
Let's not do that.
we're all looking at them together. But I appreciate the effort.
Yeah.
Okay. Consider the following Java method calculate. So it's a dual recursive function, I think it's called. A binary recursive function. So the base case is if n is is less than or equal to 1, return n. Otherwise, it will return calculate n plus 2 plus calculate n plus 1. What growth rate corresponds to the tightest big O time complexity of the method calculate as a function of its input size n?
N squared, right?
Let me actually draw this out. So imagine we have like 3.
10. Oh.
Or yeah, let's do 5. I don't want to type too much because it will take too long. But 5 is a good number, I think. So it will do calculate 3, and calculate, and calculate 4. Calculate 3 will do calculate 1, calculate 2, and calculate 4 will do calculate wow, I literally had to think about what calculate 4 would do. Calculate 2 and calculate 3. Then calculate 1 will return. Calculate 2 will do calculate 0, which will return as well. Oh wait, I shouldn't put it there. So calculate 2 will do calculate 0, which will return after this, but we are not there. Calculate 2 will also do calculate. Next time I'm just gonna call it C instead of calculate. Calculate 1. Calculate 2 will do calculate 0 and calculate 1. Calculate doesn't even look like a fucking word anymore. And calculate 3 will do calculate 1 and calculate 2. And then calculate 0 will return, calculate 1 will return, calculate 0 will return, calculate 1 will return, calculate 1 will return, calculate 2 will do calculate 0 and calculate 1, and that will return and that will return. So all in all, we have 1, 2, 3, 4, 5, 6, 7, 8 calls for 5. And if we
time
look,
complexity also includes the calculate functions, I believe.
Mhm.
That also has to run. So I wouldn't say, because I think what you're doing would work for space complexity, right? Because you're looking for total calls. But
Yeah.
yeah,
I
okay,
think what you want is all the calculates plus all the returns, because every single one of those is a calculate function.
yeah, that's true. It has to add something which is linear indeed. Would that
So
matter
it
though?
is-
Because especially if we're just comparing stuff, it's just gonna be like, so we'll have
is
to
it not
multiply
just,
everything by 2. Well,
sorry,
okay,
does it
not
not just look
necessarily.
like a binary tree with height 5? Like, can't we just say it? We basically just have 2 to the n, right?
Yeah,
the
yeah,
end
yeah,
call.
yeah. You're right. Yeah.
Yeah, that actually makes sense because, like, I was thinking about the left side how it would decrease faster, but the height of that of set 3 would be just because every time calculate is called, it will go to the right. So 5, 4, 3, 2, 1, 0. Or actually, because it's less than or equal to, it would be of height n minus 1. But still, I think that would indeed be.
It is a binary tree with a chunk out of it, but the chunk is like probably a constant or something like that, so it won't change the fact it's exponential.
Yeah. So that means how many calculations are there? Would that be 2 to the? Yeah, okay. I mean, all in all, just by looking at it, at n is 1, it will be 1. At n is 5, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. It scales pretty quickly. So I think we can safely say it's D. On a test, I would actually calculate, do like maybe 1 and 3 and then 5 and see how they scale in correspondence to each other. But the chat made a good point about about it being a binary tree, which is just 2 to the power n.
Yeah, it's helpful to draw a recursion trace of that kind of stuff. And that way you can see what shape it has, which in this case is a binary tree.
Yeah.
Yeah, I mean this is just Fibonacci, so.
Yeah.
Yeah.
Okay. Consider again the method calculate as well as the method calculate 2. Which of the following statements is true about calculate n or calculate 2? So if n is less than 1, it will return n, 0. A temp value is when it's called on itself with n minus 1, and and the return value is the first value of that plus the plus the second value of that, comma the first value of that. So let's see what's true. Okay, so both methods calculate and calculate 2 use binary recursion. Well, that's obviously not true because there's only one call here. And this is like, by the way, this is more like the standard version of Fibonacci you would see in, like, for example, Python. In like a for loop without using recursion. So yeah, so D is wrong. method calculate 2 uses more stack frames than calculate. Well, that's wrong too, because there's less recursive calls. Because in this place, there's literally only n recursive calls. Method calculate 2 runs in big O of n time. Would it?
Let's look at A first.
Okay, method calculate uses tail recursion, method calculate 2 does not.
I think it's the other way around.
Yeah.
Yeah, it's the other way around. So
So method calculate uses tail recursion, and method calculate 2 does not.
I think it's the other way around. I think
the other way
calculate
around,
2
yeah.
uses.
Method 2 uses skill recursion, method calculate 1 does not, yeah.
so B.
I'm pretty
Yeah.
sure it's B.
I'm pretty sure it's B
Because
too. Because
it's,
there's
it's
just like,
single recursion with n minus 1, so it should
yeah,
be B.
it's like there's
All the
n
rest
there's
is
n stack frames eventually with this one, or at least big O of n, and
Yeah, no,
everything in here is constant time. So yeah, Sive is just B.
How many questions are there?
I don't know.
On page
Oh.
2 of 8.
Page 2 of. Oh wow, that surprises me. The answer sheet has 22 pages, so I thought there was going to be like 20 page questions first.
I think
but
it's
not.
25, out of which 3 are open.
I see.
Right.
Okay, so we've done 5 and 6. Let's have a look at 7. Which of the following average time complexities does not involve probability or probabilistic analysis? Big O of n for getting an entry from a hash table, but then we're looking at the probability of the hash of that hash being already.
Everything with hash tables is probabilistic.
Yeah. For adding an element at the end of an array list implemented using a dynamic array with proportional resizing. Well, that's also got something to do with probability because it's the chance of the
the
chance of it getting resized.
Isn't that more like amortized complexity, not necessarily probabilistic analysis?
It says average case time complexity, so it doesn't involve that for the dynamic array. It's not it's not probabilistic on average.
on
Because
average, there's like
amortization takes care of making it like constant time on average.
Yeah, but to find out that the average time case is 01 involves probabilities, because the probability of it having to rescale is 1 divided by n squared or something. I'm not sure. It's log n
Depends
or whatever.
on what amortization you use, but yeah.
What about the rest? So we have randomized quicksort, and
that's definitely probability, because quicksort is inherently random. Or quicksort is inherently random. Sorry.
Yeah, but quick select is that? Well,
Never heard of it.
It says randomized, but it might be a trap.
I've never heard of it.
I mean, there are 2 answers which are random, so one of them is a trap.
But if you put randomize, it's already probabilistic because we're choosing something on random, which is probability based. We can't just.
B isn't random.
I see. I think out of all of them, indeed, B is like the one that has the less chance to be wrong, and I kind of want to finish it.
It's not random, so it's not based on probability.
Yeah, exactly. It's you take an average.
Yeah,
of,
okay.
Of
It's
the
not.
amount of
It's indeed not
operations.
random. It's like systematic. Like
Well,
every n
amortized,
times.
that's what it means. So
Yeah, I see.
They ask about the average case, so it's not random.
I see. Yeah, out of everything, B is the least random in my opinion as well, and it's just that makes sense. Okay, which data structure are used for the following task? Expression parsing and breadth first search. So we can look at breadth first search. Let's see. There was this thing about
for expression it's stack.
Traversal. It was somewhere in the later chapters.
I think it's
in
trees.
Trees, probably. Tree traversal algorithms. Okay, what was the question again? Which data structures are used for breadth first search? So we're gonna go to breadth first search.
Breadth first is by level, right? Yeah.
Yeah, there we go.
First stack and then queue.
And you can see it initializes a queue and a deck. So we know for a fact that breadth first is queue. I already knew that because I implemented this before, but like it's still good to just know where to find it. And for parsing, you use a stack, which makes sense because when you add like the last opening bracket, you want to be able to retrieve it as soon as possible again when you're getting the next closing bracket. And using a queue for that would make no sense at all.
Yeah, and if they don't match.
It was
Parser
also in
goes-
Joanna's video, I believe that's that example of a
Yeah, okay.
stack.
That's fair. I just yeah,
Like,
okay. I just
okay,
knew that it would be, but like if it's already in the video, then you know we already know it. But like if you use your brain for a bit, you can also figure out that like using a queue for this would make no sense. You're gonna have
Yeah, I try to prevent that at all times using my brain. Yeah.
that is
so-
true. That is true.
This might sound stupid, and it might cost me like 2 to 3 minutes, but I remember that it was said in the video. So at this point, I would go to the videos
Yeah.
and look
Valid.
which one has a stack in it.
What happens if we look for expression parsing? Oh, sad.
And if you just look for parsing or just for expression, expression won't work. But
Yeah. Yeah, no, just parsing won't work either. That's like way too broad. But yeah, it's probably not mentioned in there, but you just using your brain, you can figure out it's a stack because you want to get the first closing bracket when you're there.
can you look up matching parentheses? Because I do remember it, like seeing it. Stacks.
Man, that's sick. It's actually in the book as well. Nice. Okay. 9. Which of the following statements presents an implementation of a priority queue from most to least worst case time efficient left to right for an insertion operation? From most to least efficient. Well, I guess inserting in a sorted list would mean you'd have to imagine if you inserted that in the front and then you go, it's like for example, the biggest element. Then you'd have to go through the entire list. So that's like big O of n. That's pretty bad.
Check the general VC.
General VC.
This is why you have notes, people.
Okay. Let me open that up for you. So this is a screenshot from the slide. Really useful to have.
Yes.
So it would be a unsorted list, then a heap, then a sorted list. However, I think I will be able to deduce this as well, which is useful because you can get far with only using notes and books, but being able to deduce stuff helps for especially the open questions.
Yeah, especially because like, you should be able to know that it's either C or D first, because we're an unsorted list. Insertion is really easy.
You just slap it in the
Yeah.
back.
Yeah, and like I think it's D because like if a sorted list was more efficient than a heap, people would use a sorted list. But I think a heap is more.
We know that heap is always log n. Everything is log n, and for sorted lists.
Well, I mean, heap is like the min of or the size or the empty is is O of 1.
Yes, but like the important stuff.
Everything for size and is empty is all fun.
Yeah. But okay, realistically speaking, unsorted list, we already know this one is easiest. We know a sorted list in the worst case, because they're asking for a worst case, is the hardest, because then you'd have to go from
the first to last.
Yeah, then you'd have to go to like all the way to the back if it's the lowest element. So this is like big O of n, and then you know the heap is probably somewhere in between. And that's just like either intuitively or you can know that down heap bubbling or up heap bubbling or whatever is big O of log n. So let's see, that is the answer to 9.
Right, we're already at a third. Woo!
Woo! How much time do we have for the exam?
3 hours or something.
Yeah, but don't forget that 3 of the questions are open questions, and generally the open questions.
That's gonna take a lot longer. Okay, consider the clone methods below from cloning objects of class singly linked list. Okay, so what it does is it creates a singly linked of entities. I thought it just calls super.clone and it's just done. I guess this just clones the first node then? Or what do you guys think with super.clone would do?
I don't know.
Because before we know what super does, we need to know like what.
Doesn't it call the class it inherited from?
Yeah, exactly.
And
But we
then
don't know
it
what
calls the clone method from that class.
Yeah, but we don't know what it's inherited from. That's the thing.
We can check the
From the objects class,
documentation.
probably.
So it would call object.clone.
Probably.
Yeah, I guess I don't
But
know.
maybe
That's the thing.
maybe that's just a detail. Maybe it doesn't.
Yeah,
have to
fair.
call
Yeah, I would. Weirdly enough, I would look at the questions first for this.
I'm gonna go through this first, and then we'll see if we can get it. So if size is bigger than 0, the new list dot head is a new node, which takes the head of the.
Just
I
copy
assume
the
that this head is just a property
It's-
of the list we're in.
Yeah, it's
So
a
then it just
method.
does head
So
with get element, and then the element after that is null. Then it gets the next one. Then let's see, other tail is other.head.
Yeah. So
But isn't that like the one we just created?
No, they're preparing for insertion, I think.
yeah, just read the while.
I see. So while walk is not null, it goes from because it goes from the tail to the head, and then it just copies every element one by one. The newest is new node walk.get element null. Then yeah. Okay, so basically walk is just an element that traverses through the singly linked list from back to front, and then every time until the walk is 0, which will be when it arrives at either the head or the tail, looking at how you look, depending on how you look at it. It will just get the next one, assign it, get the next one, assign it, take the next one, assign it. Okay, cool. If a node of the clone list is replaced, the corresponding node in the original list will also change. That is absolutely false. Because
It's
yeah,
a
it
div
just creates
copy,
new
so
nodes.
that's how copy. So yeah.
Yeah, it just
They're
creates
not
new
related.
nodes and it copies the element. So if it will be an element of I don't know, arrays or anything else that's like passed by reference, and you would change that element, then yeah, that would be changed. But the node itself, no, it's just a new node. Okay, if an element of the clone list is replaced, the corresponding element in the original list will also change. This one has a quite a bit of potential to be true because of what I just said. Okay, if an instance field of an element in the clone list is changed, then the field of the corresponding element of the original list will also change. I'm not sure what an instance field is, but I'll get back to that. And if the head of the clone list is changed to point to the tail of the clone list, then the head of the original list will point to the tail of the original list. This sounds like a bunch of bullshit. It's like, yeah, this doesn't sound like it would make any sense.
Yeah, this is not true for sure.
Yeah.
I think what they
I'm not
mean
sure
by
if
instance field is like if the linked list kept a size property. Like just a property.
a property of the new list.
Yeah.
Okay, yeah. So that would not be true, and we already, at least I was already leaning towards B because as I just said, if an element that is passed by reference.
Because it's a new node and not a copy method used.
Yeah, exactly. The element itself doesn't get duplicated. It's just the reference to the element that gets duplicated.
Would that only work for a positional list?
What do you mean?
Well, I believe that a position is specifically that thing that had the property where the element could be changed, but the position itself does not change. So we copy its position, but the element it points to, which we just talked about, can change. So
I think this.
Is this only valid for a positional list? That's basically my question.
I see. Well, I'm gonna be honest with you, Chief. I've seen the position stuff pop by in lectures and in things. I have no idea how they work or what they do.
Oh, actually, I think it's C. Because what we do here is we change. Like we don't know what are the fields of this linked list class, and when we clone it.
The
We should- Yeah, go ahead.
sorry, instance fields are the basically the variables stored in an object.
Yeah, but I mean, we don't
So-
know what they are for this concrete class.
Yeah,
I mean,
we know
if
they
it's-
are cloned by super.clone. Like
If
this
the-
probably it probably makes sense because the singly linked list inherits from something else, and those properties, so those instance fields, are getting cloned by super.clone. However, once this thing is done, and the in the clone list, if you change one of the instance fields, they will not
No,
be the same.
it's asking about the instance fields of the elements, which means that the
Ooh.
elements are objects.
Oh, true.
So
I see. I thought
if
it's the
those
instance field
objects are
of the clone list.
Yeah, it's the instance fields of the elements themselves.
Yeah, then I think it's even more true that it's C.
Yeah,
No.
it could be C then. Now that I think about it.
In B, it's if an element is replaced in the clone list, it shouldn't matter to the other list because we
Oh,
don't
I see.
change
Because
the
it's like
actual element.
if the element is changed, that means like it references another element.
Yeah, so
And
we
then,
don't
yeah,
change
then it
the
doesn't
actual
matter.
element, so we shouldn't.
But if like an instance field of said element that is being referenced is changed, then the original one will also change.
Yeah,
I see,
then we
that makes
change
sense.
the properties of the actual element.
Okay, that's
so
good.
if something references it from the other list, it's fucked.
Yeah, so we'll call it C. Okay. 11.
I think you just typed
Yeah.
C after question. Yeah.
Yeah.
That.
Excuse me. 11. Consider an array-based implementation of a binary tree. For which kind of binary structure does this implementation of the use the least space in absolute terms, not asymptotic? Well, the thing is, so I don't know if you guys remember the array-based implementations of binary trees. Oh, but I'm gonna bust the good old paint.net.
Can you go to the book and show the definitions of proper and complete and etc. after?
A proper tree is a tree for which every internal node has exactly 2 children.
Oh,
Therefore, a proper tree is so, oh god. Let me see if I can find a proper tree.
Yeah, this one.
This one would be a proper tree.
Yeah.
And a complete tree, all layers are full, basically, except for the last one, where they're all left.
Let's see. So we have a proper or full binary tree. Are they synonymous then?
No. A proper tree, there's no empty space. So, say you have an array, there's no empty space in that, just at the end. All the layers are full except for the last one. They're all the way left.
Yeah.
No, they don't have to be full.
I think
proper tree.
I think they do have to be full for a
Having
proper
two
one. A
children
complete
and
one
being
can be not full on the last layer.
Because you can make one that is just 2 children, and then the right child has 2 children, and then the right child has 2
Yeah,
children.
yeah, exactly.
A lot of
Yeah, there will be a lot of
yeah.
Okay, so then we have a complete binary tree. So wait, what the fuck is a general binary tree? Sorry, a complete binary tree, which is from what I remember, a tree which every layer except the last one is full, and that one just has all the nodes to the left as possible.
Yeah, then this is.
That's the answer.
Yeah.
However, we will also go over the other ones. A balanced binary tree, but yeah, that doesn't make too much sense because you can have a balanced binary tree that has empty space in the middle, which will leave empty space in the array, and a degenerate binary tree in which every internal node only has 1 child.
What? No idea.
Yeah, no, this.
Sounds inefficient.
They're talking about internal nodes. So does that mean like the
Every node except for the external nodes.
Okay, I see. Thank you. Every internal node only has 1 child. Then
I mean, it's basically every node has 1 child, so it's like a.
That's basically a unary tree.
Line.
Yeah, it's just a line. But consider an array-based implementation. But here they're saying a binary tree. Okay, I see. So you're still using the binary tree to array conversion thing. Because like in the case you indeed have said thing, so you just have like a few lines going like this to, for example, say we go to the right every time. that's still not very optimal, because you will have like a bunch of space left, and even if you do the same thing with to the left, as long as you're using the arrow-based implementation of a binary tree, then yes. If you use the array-based implementation of a degenerate tree on a degenerate tree, you just have an array. But I think at the same time, like, for now, the complete binary tree would make the most sense, because a complete binary tree would look something.
A complete binary tree would also just be an array.
Yeah, exactly. A complete binary tree is an array, but then like this one actually gets implemented properly. So imagine a complete binary tree could be like this. Let me actually bop 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 bop. This would be a complete binary tree, and I think the labeling of it would be like 1, 2, 3, 4, 5.
Zero based.
Okay.
Zero
Yeah,
based.
it starts with
coming in
zero.
hot.
7, 8. So this thing has 8 nodes and only takes in 8 spaces, which is exactly what we want. However, if we had like the same thing for a unary tree, we would only have 1, 2, 4, 8, etc., and that would leave like a bunch of space. This was like the least efficient thing you can think of when you're using that array-based implementation of a binary tree.
I mean, it. I do agree this is the most efficient, but didn't they say that with like it isn't all the fields are full? I believe, because I believe they said that, and correct me if I'm wrong. But if with a array-based implementation, every time you add a node which is over the last list, there are still room reserved for the next like 7 nodes here. Or there is still room reserved.
Is it though? Because I could understand that like a if it doubles in size every time you add a new layer, then this would not be a good idea. But
Well,
does
it
though?
is. That's how these are. I mean, I guess if they ask for the least space, they don't have.
Isn't it the same for all the trees though?
Well, with balance, there might still be holes somewhere. So with balance,
Yes, it's less efficient.
Yes, best balance less efficient.
I guess the least space means there's the least amount of new values in the array.
Yeah, I guess it would mean that.
I think the least. I think. Okay, sorry. Did I speak? Hello?
Yeah, sure.
Basically, what I was saying, if I what my idea of least space is, there's no gap in the middle of the arrays.
Yeah.
And complete array is the only one that fills the array fully, and then maybe there's like a little space for the next elements if you add newer ones.
Yeah,
I think that's why complete binary should be there. A balanced one will have gaps in the middle, and a degenerate will definitely have gaps in the middle, because when we do like the array based where we do 2 times the parent node plus 1 and plus 2, if we have like spaces, then the plus 1 or the plus 2 will be empty somewhere.
Exactly.
So that will like be in the middle. That won't be like space efficient compared to where we fill all the first, then we have a little more space for the next few elements.
Yeah, exactly. Like in a list here, this would be like a list of like 16 elements. Please mute yourself.
Okay.
And it would be a list of 16 elements, and it would only have 4 used. This sounds absolutely atrocious. Don't do this. So I think the answer would be B. For 12, which statement about tree traversals is false? It is possible for the post-order and pre-order traversals to visit the nodes of a tree with more than one node in the same order. Well, I mean, that's true if you just have a tree with 2 nodes.
Yeah. Or
well, actually,
say have a look at post order and pre order.
So imagine we have this tree. This is my amazing tree. So in pre-order, it would visit this one first, then this one, then this one, and this one, then this one, then this one, then this one, and this one. And then post-order would do like this one, this one, this one, this one, this one.
No, that's in order.
No. You can just draw the line
first
over
visit
the
the childs and then the parent.
Yeah, but still, even if you had a thing with only 2 nodes, the post order and pre-order would not be the same.
No.
Okay, so this
Yeah.
one is false. Well, that
Right,
one is
so
false.
then we're done. But let's
look at
check the other one. Yeah.
It is possible for post order and pre-order traversals to visit the same nodes of a tree. To visit the nodes of a tree with more than one node in reverse order.
Yeah, true.
Yeah, with 2 nodes it's possible.
Yeah, with 2 nodes, that makes sense. It is not possible for post order and pre-order traversals to visit the nodes of a proper binary tree in reverse order.
Which one was proper again?
Proper is like every node has 2.
Everyone has 2 childs, so just add another child to the last node, the first leaf, the leftmost.
What do you mean?
Like
this?
Yeah.
Yeah. Oh.
That's the odd child. It's a line.
Yeah. It is not possible for this to visit the nodes of a proper binary tree in reverse order. Oh yeah, and like for the last one, real quick, in order traversal is only defined for binary trees. Well, that's true, because if you had like a unary tree, you can't do it in the middle of nodes, and if you have like a tree that is 3-way, then it also wouldn't work. So yeah, I'm pretty certain it's A.
Codes. The reverse order you have on for C. It's not possible.
What did you say?
I was just thinking about C.
Okay.
I mean, it doesn't say that the post order and the pre-order need to go in the same direction. Like if you do your post order from the left and your pre-order from the right, could you then, in some sense, have a reversed order?
Very convoluted, but
You always start your traversals at the root, so I don't think.
I'm pretty sure with pre-order and post-order they mean the standard pre and post-order ones, namely left first.
Well.
I mean, if you start it from somewhere else, that's the root. Wherever you start it, it's considered the root. It doesn't go upwards on a tree. It's a subtree traversal. Like if you start, let's say at 15, you'll never go to 25 in any order traversal. It doesn't even know 25 exists.
Yeah. A pre-order traversal and a post-order traversal. Yeah. Wait, there was a better image for this. Let's see if I can find it.
I mean, the book has images on all the traversals.
Yeah, that's a good one. Let's actually have a look at that. So it is tree traversal algorithms. There we go. Dude, that's fucking sick. So this is pre-order. And then see about post-order. Breadth first, in order. What's this? That is still in order.
You missed it behind you. It was back.
Oh.
Just do Control F for post order.
The thing with Adobe, like looking for stuff in a PDF file, doesn't really work that well.
Oh.
Okay, so let's see. This is in order. This is breadth first. This is post order.
Behind this, yeah.
Then it should be there. Yeah. Okay. So this is
This
pre-order.
pre-order.
This is post order.
Yeah.
Yeah. Okay. So the only difference is like here it does this one first, then that, then goes to the next one, and here it does that one first, then that, then this one, then goes to the next one. So the way like yeah, I see. Okay. How does that relate to our question again? It is not possible for the post order and pre-order traversals to visit the nodes of a proper binary tree in reverse order.
For them to visit them in reverse order, we must have the post order one to first visit the right child and then the left child.
Yeah, indeed.
Which never happens.
Exactly. Yeah, that makes sense. Because if it only had like 2 nodes, say only title and extract, it would be paper, title, abstract. And for it to be in reverse order, it should be abstract, title, paper. which doesn't make any fucking sense.
Yes,
So-
since it's what is it, a complete binary tree? It's never possible.
A proper binary tree.
Yeah, whatever. Anyway,
Yeah. So I think it's just A.
as long as there are no just a single child, it's probably impossible.
Yeah. Consider the sorting of a sequence, blah blah blah, in increasing order with in-place heap sort algorithm using an array-based heap. What is the content of the array after the first 2 removals from the heap, including the necessary bubbling operations? Let's see. An in-place heap sort. First, the content of the array after the first 2 removals from the heap, but there's still the same amount of elements.
Yeah, because what
Because
in
this is in
place
place.
does is it takes the so yeah, it takes the first element, puts it in the end of the takes the second or takes then the first element, puts it on the end, I think. Yeah. Anyway, the reason is because you're looking at both the input array and the output array.
Oh, I see. Okay, that makes sense. And then the heap would take take like the rest of the not yet sorted space, right?
Yeah. So,
imagine if we have like an array here that's like this long and has like these fields. At first, then the heap would contain all of these, and then after the first remove, let's say the biggest element would be here, and the heap would just consist of these 4 spaces.
Yeah,
and then
and,
like 9,
so-
and then these 3 spaces, etc.
Yeah, so what it does is it takes the first element, or it's a max heap. So the first element's always the highest. So you take the first element, put it
Wait,
in.
did it explicitly say that it was a max heap?
It is a max heap because you can see at the end we're going for the max.
Well, but that, here it said that the first, like, it could be this one as well then, because then at the start there's 2.
No, but to do, I guess it would be possible if you take like the last one. No, because it's an array-based implementation. The first thing will always be the top node, else the position of the top node will shift, and that doesn't work. So it could be the other one if it was a different based heap implementation. But since it's an array-based implementation, the first node is always the highest one, and that's the only one you can reliably access. So that's the one you want to have the highest.
I see.
So first, the 12 gets moved to the top as it is, as it gets like bubbled, whatever.
Yep.
So that gets put at the end. Then the 9 gets bubbled and put at the end. Then the 7 gets bubbled and put at the end. So it's either B or C. The real question is, how would this end up? So for this, I would actually draw the heap and work it out from there.
Okay, how many elements does it have? 6. Let's see, so what were the restrictions on the heap again?
It's a complete binary tree, I believe.
Yeah, a heap. So there will be priority queues and heaps. What is a heap? Heap properties. It has a structural property. It's a complete tree.
Yep.
And a relational property. So the thing above it is higher than the thing below it because we're using max heaps.
Okay.
Guys.
Yeah.
You know the Ludo game, the Ludo-tastic?
Yeah.
I broke it.
Epic.
Of course.
They're just.
We're in the middle of a recording, so like you can talk to that about that afterwards.
Somewhere else.
But for now, yeah, we're just gonna continue with this.
Fine.
Talk about it in in the WDT channel.
Yeah, talk about it in WDG because I am interested in that because I was looking at it trying to break it as well, but I couldn't. Okay.
Okay.
So let's see. We start out. So the thing above it is the highest.
So yeah.
So in that case, this would be Well, I mean, since 9 and 12 have already been removed, we can just implement the thing of the of like the case where 7 is the highest number, right?
Sure, yeah.
Okay, so then we have 7, then we have like 3, then we have 4, then we have 1.
That's a valid heap, so that's correct.
Yeah,
And try with the other one. No, that one can't be correct because
Yeah.
it's 7, 1.
So then we have 7, 1, 4, 3, and this doesn't
And that's
make
not a
sense.
valid heap. So it has to be C.
Okay, good call. I am still learning so much, by the way, here. Holy shit.
I am just reading off from my fucking notes, which I made painstakingly over the entire quarter, and I'm so happy with them.
Consider the following method C-sort, which implements a sorting algorithm. The input array is guaranteed to contain integer values between 0 and k.
Is it? Oh, never mind. I was about to say, is it? Are they distinct? But no, because it's a value you can repeat because you're just given k.
Yeah. Okay, so it's public static void C-sort. So a temporary array is created, which is k plus 1 elements. Well, that makes sense because it's 0 and k inclusive. For an array.
For every element of the array, make it increase it by 1 and
It's
put
a
it in
bucket
the temp
sort.
array.
Yeah, you're just counting how
it's not
many
increased
of
by 1, it's
each.
just its index value by 1.
Oh yeah, you
Yeah, I didn't know if this would like. Oh wait, yeah, okay. So I didn't know if like this creates an array of integers, but I didn't know
Yeah.
if those integers would automatically start out at 0.
No, it's just empty.
Yeah,
Or
but-
actually, I think because it depends which language it is. Really.
Yeah, but it's Java. I think they start out at 0. I would myself put like a thing here that went through all of these and made them 0, but apparently that's always the case. So here, this indeed just goes past all the elements and then makes the each elements, for example, 1 higher. So for example, if we had like 1, 2, 1, and the k was 2, after this the temporary array would be 0, 1, 2, 1, 2, 1.
You know, I really like the sorting algorithm. I don't know what it is, but it's fun.
Yeah. Then they have ndx. Then they say for I is 0, I is less than temp length, I plus plus. So this is just I is less than k plus 1. While temp I is less than 0. So they go over all the things.
It's greater than 0.
Oh yeah, excuse me.
So while there's still things
yeah,
left in
okay.
temp I, yeah.
Yeah, so the
Oh,
ndx
this
is just
sorting
like
is pretty cool indeed.
yeah. So the ndx is
And
just like a
It's a
position.
current pulse. Yeah.
Yeah, I
They
would
just
call
make
it
a-
current pulse or I or something like that.
Yeah,
And then
same.
they just say, okay, current pulse ndx is equal to I, ndx plus plus. So the current we go to the next position in our array and decrease the temporary array I by 1. That's pretty fucking smart. I like this algorithm. This is a cool algorithm.
Yeah, it
My
makes a
stamp of
height map
approval.
and then empties it.
Yeah. So, which of the following statements about the method C-sort and a sorting algorithm it implements is true? It is a comparison-based sorting algorithm. Wrong,
False.
because there's no comparisons.
Well, there's one comparison.
Yeah, okay.
I smaller than temp length
Yeah,
and temp
but
greater, but that's not
a
comparison. Yeah, you're,
Yeah, it's not
you're not
comparison-based.
comparing different values.
Yeah, it doesn't compare two elements in the array.
It is an in-place sorting algorithm. Look at the
Definitely not.
second line.
Yeah.
Look at it.
It's first line of the algorithm, yeah.
Yeah, and not only
Yeah,
that,
line
like
two.
they say it's O1 space complexity, but it creates a new array of integers. So I mean,
With length n, so
Yeah,
it
with
gives
length
it to
n.
n.
exactly.
Yeah.
It runs in O(n) time, where n is the length of the input array. Well, here it goes through the entire array, and here it does it again. I mean,
So that's 2n.
that's 2n,
that-
but
2n,
2n
that's
is big
fine,
O of
right?
n, so this could be true, yeah.
But
at
in
each
the for loop, which runs n times, you have a while loop, and does that imply that it can be?
Well,
Yeah,
if
we know
there's
we know
only
for a
one
fact
type of element,
we know for a fact that the total sum of all the numbers in temp combined will be equal to n.
yeah.
And this stuff just gets accessed, like the total amount of numbers in the or like the total sum of the numbers in temp times, which is just n times. So while
And-
this may look weird, this is just big O of n.
Yeah, let's
Yeah.
say the original array is just 5 of the same number, then you have an n squared, because it will just cycle 5 times into this while.
Not really. Like, yes, it would cycle 5 times over this while, but it would execute. This thing wouldn't execute at all for the rest of the stuff. So then that would be 5 times a constant.
Yeah, what I would think,
but you already done the n squared part. So
how I would see it is every time it runs that bit of code, it changes one thing of the array and moves on to the next. So every time that piece of code runs, it finalizes one of the final array. So
Yeah,
it
which
cannot
is-
be more than n, because then it would have to run over the array twice or n times, which
Yeah.
it doesn't do, as evidently it only goes over every element once.
Yeah, and like, let's say like this, we already know the total amount of that ndx will reach is the total amount of integers in the original array. However, if we didn't know that, then this would eventually just throw an array out of bounds exception. And
Yeah.
since it probably doesn't, we know that this thing only gets executed n times.
So 3 and
Yeah,
4 is
that's
n times, and 7 to 12 is n times. So total of 2n ish.
Yeah,
So ON.
I would call this if I had to do an actual like analytic
It was
yeah,
CN
analysis of this,
ON.
I would just call it T
CN.
of n is 2n plus c, or
Yeah,
2n times
technically it
c1
runs-
plus c2, something like that.
Actually, I think this algorithm doesn't even care about the length of the array. It runs on
Yeah, it does,
the
because it
K.
goes through the entire array here.
Yeah, there, but the rest of it is K based.
Well, no, because the you can see that the array ndx runs until they've had every element, and every element will be. So, like I said, it finalizes one of every element in the second part of the loop, or second part of the thing after the line break.
Yeah, but I mean, this is not
Yeah, it iterates
dependent
over.
only on the length of the array. It's dependent on what K is.
No.
Yeah,
Yeah,
it
because you can
iterates
calculate
over
that
an
NDX
array
will always-
whose length depends on K.
Okay, let me get this clear. So, this loop indeed matters on K, because temp length is K plus 1. However, this code in here, which is the only code that actually gets executed except for this, which is constant, this only happens when temp I is bigger than 0. And temp I is bigger than 0 only n times, because we make it bigger than 0 here n times. So this stuff only gets executed n times. And that's what we care about. So this stuff is big O of n. This stuff is big O of n. Add them together, still big O of n.
No, the other part is the for loop is n plus k.
Yeah.
Oh, it's
It could
Yeah.
be like if because you look, if you have an
Let's say-
array
let's say
with
like
size
K
1 and
really
give a K
large.
of 1,000.
Yeah.
Oh wait, no,
that's
because
still
n
big O of
is
n.
guaranteed, but n is guaranteed to contain integer values between 0 and k. Would that change anything about the
Not
fact
really.
that it's n plus k?
It
Well,
would.
whatever. We know it's on time.
Yeah, we know it's O n time, because
No,
even
no,
if
no,
it's
it's not. No, it's not.
even if it's big O of n plus k, the only way for this to be more than O n.
Yeah, if
then it has to
k
be
is
O n
larger than
squared.
n.
Okay, can we look at the next?
No, if you take for example that n is like 100
D.
and k is like 10,000,
But
then it's not going to be ON.
the input array is guaranteed to contain integer values between 0 and k. So
Yeah,
n
yeah,
equals
the
k.
values can be between that, but n is the size of the array, the number of values we have.
Yeah.
Yeah, I see his point, though I'm not sure
Yeah.
if it matters if you're looking at C, because they only tell you to evaluate it on basis of n. Let's look at D. If it's not D, then it's C. If it is D, then it's not C.
Yeah. At each index, the array temp accumulates the number of elements from the original input array that are identical to such index. Ooh.
This is correct.
Yeah, that seems correct.
Has to be correct.
At each index, the array temp accumulates the number of elements from the original input array that are identical to such index.
It basically becomes
Yeah, okay,
a
that's like
height
this
map
line.
of the original array. Yeah, it does
Um,
part of the sorting algorithm.
I'm not sure actually, because do they mean this like at the end of the program? Because that's not true. Then it will be 0.
No, it's
But-
at each index, which I believe they're talking about the index at line 3 and 4 or 4 and 5.
Pretty much the first 4 loop.
Yeah,
so
No, but
this,
what
this
he's
thing
saying is
indeed
that
does this. So it might actually be D then.
Then it is
D is true.
no, but what
These
he's saying
ones
is
that
that
looks
by the
true
end
to
of
me.
the program, temp is empty. It's all going to be
Yeah.
zeros, right?
We're gonna call it D and then just have then just look at the answers afterwards.
This is a very weirdly asked question.
Yeah, exactly.
I wouldn't be surprised if they did both C and D correct in the answer
Yeah,
sheet.
either
but we'll
that or they would say that this is like big O of n plus k, but at the same time,
I
But
think
the
quite
thing
sure
with
it's
if
like
we're
D
doing it by n, k is
It is.
considered a
no,
constant.
It's basically a bucket sort.
yeah, it is.
So on
But
plus
the
k.
problem with C
Yeah,
is
okay.
that it can be like more than like, so the K can be have a value more than N, and that can cause like
Yeah,
a
we said that.
being O(n) can be O(n) squared, because if we
Yeah.
assume K is equal to N.
I
So
think
it can be
realistically, what
L.
we're looking at
D is
realistically
true
is
for
just
all.
the fact that this is bucket sort, and bucket sort is big O of n plus k.
Yeah.
So I think you're right.
Wait, guys, no sorting algorithm is ON time, right? You can't have a sorting algorithm in ON
Well,
time.
the thing is,
Yes, if we
you
have the
can,
arrays specifically.
but the problem is that they exist, but they all have drawbacks. Like for instance here, your input value needs to be between two values and or between k values, and you've got other, like I believe radix sort also has something like on, or I'm not entirely sure, but it was also something very low.
It's also
Yeah, O of n plus capital N. But like, then again, it is dependent on other stuff. So with arbitrary data, the lowest we have is, I believe, n log n.
Yep.
But with specific data, you can get the time lower.
Yeah, it's like partial sorting. Maybe
Okay.
can be ON, but not
Okay,
Yeah.
let's go
general.
to
Let's continue because I want to be done until the 3 hours are over. Consider again the method given in question 14 between method csort and complex and algorithm merge sort. Which one is the fastest running time for each of the following situations? First, running 1 million bytes, sorting 1 million bytes, which are valued with a k of 8. And second, sorting 100 integers between the range of 1 and 1 million. Well, since we have concluded that this one is big O of n, we need to find out what the big O of merge sort is. So we can have a look here.
In log n.
what is it? Worst case or best case? Actually, it's n log n in both times.
Yeah.
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 Let's see, where is it actually? Oh, it should be on the right here. So merge sort is n log n.
Yeah.
Okay, so this is n log n, and the other one is n plus k. So looking at it, this would be, so the first algorithm, our algorithm, would be O of how many bytes were there? 1 million. So the first algorithm would be O of 1 million and 8. I'm not sure if that's the correct amount of zeros, but frankly I do not care. And in the second case it would be 100 integer between 0 and a million. That would be
100 plus a million.
Yeah, a million plus 100. Cool. The second one would be merge sort, and that's n log n. So that would be a million times the 2 log of a million.
I think writing it as 10 to the power of 6 would be easier.
The thing is, it's like the 2 log, not the 10 log.
Yeah, but
Okay, just representing it, it would be easier.
Yeah.
I think I forgot a 0 here or whatever.
Are you really gonna be calculating log 2 of 1 million?
Let's see. So we have the
Well,
answer
we
like.
we know that it's larger than 1.
So yeah, this thing, the 2 log of this is like what?
It will be at least like 8 million or something.
Yeah, it will be at least 8 million, which is bigger than the 1 million. And for the second case, it will be O of like the same.
Yeah.
Times log of.
No, it's 100.
No, it's 100 this time. And it's 100.
Because n's 100.
Yeah, so it's 100.
Sorting 100 integers
log
in a
100.
larger range.
Oh yeah, I see.
It's 100 times log
so-
100,
Oh,
which
I
is a
didn't see.
lot.
Okay, yeah. So in the first
First
case, the R string will be faster, and in the second case, merge sort would obviously be faster.
So D.
Yeah, so the answer is D.
You know what I find weirdest about the stream? We've got people leaving and joining every so often. But
Yeah, but that happens every time.
Okay.
Ah, you must be new here.
Yes.
Yeah,
I
but
am.
I mean, they come, take a look at what we're doing. Fuck off. If they
Yeah.
don't like it.
Fraud.
Okay, which of the following statements about sorting and selection algorithms is true? Heap sort, merge sort, and bucket sort are naturally stable sorting algorithms. I don't know what that means. I'm going to go on to the next one. The time
I believe
complexion of
stable means the things that aren't changed aren't touched. So like
Yeah,
if
it's
two
always
things
wrong.
are the same. Okay,
Yeah, they
well,
should preserve the order if the elements are the same. So if you have 5 in the middle and 5 at the end, it should stay at the middle and at the end something. So
Yeah.
no, one should be on the left, the other should be on the right, even
Yeah,
if you sort.
that makes sense. Okay, the time complexity of insertion sort is big O of n plus m, where n is decided the input sequence and m is the number of inversions. In the worst case, this can be big O of n squared. That's a really interesting hot take. N
the
plus
worst
n
time
being...
is O n squared.
Yeah, this seems right.
Well, let's have a look.
What does number
Insertion.
of inversions mean?
The insertion sort. The average time complexity is indeed O n squared.
Suddenly we have.
They're asking what is true. Okay. I thought it was
You
what
can
was false.
find it in the book, it's 12.4, and it's indeed O(n plus m).
12.4. Comparing sorting algorithms. Sick. Do they? Oh.
Yeah. Wow.
There we go. The running time of insertion sort is O n plus m. Yeah, I see. Okay, cool. Therefore, we know that this is true. So we can say that it's B. We want to look at the rest of the things.
Yeah.
Okay. The quick select, merge sort, and quick sort algorithm follow the divide and conquer paradigm. Paradigm.
Paradigm.
Paradigm. I was about to say, what the fuck? That word is stupid. Merge sort does. I know for a fact, because then it just like splits it up and then redoes it, re-merge sorted.
Quick sort does.
Didn't quick select decrease and something else? Decrease and something.
Yeah. Something like that.
I have no idea what quick select is, not gonna lie.
Yeah, I've never seen it. I've seen it, but I don't remember it. But yeah, I do know that. Let's see. I think merge sort is. I'm not sure about quick sort. Not sure about quick select.
Quick sort and quick sort are divide and conquer. But quick sort is not.
Quick sort isn't.
So quick select is not. Quick select is.
Quick sort should be.
Yeah, here.
You-
Quick sort is indeed
divide and conquer.
like divide and conquer. However, quick select. Let me see. No, not search trees. It should be.
I think it's 12 as well, because I just
it?
read about it.
Yeah, because I think
12.5.
Selection.
12.5. Ah, yeah. Thank you. The bad thing about having to do this on my own is that I don't have you guys tell me where in the book something is. It's annoying.
Jure, I don't know what you're on about. Like, why do you say that you can't just use Ctrl F? Try
what
looking
I
for
think
quick
actually
select
what it
and
might be is
no,
that it's
dash, or actually both. Sorry, never mind.
I think what happens is okay. Oh wait, what? Okay.
Randomized
I
quick
thought it
select.
wasn't. I thought it wasn't wraparound, but it is. I don't know.
Indeed. It works for me. I don't know what I gotta tell you.
Okay. The quick select is. I'm getting a lot of messages. Ah, yeah, okay.
It's 12.5.1, and it's called prune and search or decrease and conquer.
Yeah. Ah, I see. So that's something different than divide and conquer. Yeah. Okay, cool. I mean that one's false. LSD radix sort may not need to process all individual keys of a composite key in order to determine the final ordering.
Yeah. For example, if you've got like 10 things and it's like 11, 23, 34. So if there's no buckets with more than one thing, it only needs to process the first key and then it's done. Because I believe it's then.
Yeah, but it's LSD, not MSD.
Oh, shit. That's true.
You guys
It'll
gotta
do
be
all
right.
of it.
And LSD needs to get all the way back to the first key.
Yeah, you're right. LSD
Yep.
is indeed, it sorts the back keys first and then the rest. Which only works
Oh
in
yeah,
standard.
okay, that makes sense. Yeah, I really quickly like forgot what LSD and MSD was, but then I realized what it is again, so that makes sense. The
I've
least
just got my
significant digit, radix sort, and most significant digit.
Yeah.
Okay, heap sort, merge sort, and bucket sort are naturally stable sorting algorithms. Well, that probably means one of them is just not.
Bucket sort.
I don't think heap sort is.
Yeah, I'm
Heap
not
sort
sure.
is not stable because it switches position. Merge sort and bucket sort are stable because it doesn't switch the positions in it. Like as in like
Oh yeah,
relative
heap sort
position is
switches
something.
position during heapify, right?
Yeah.
During the down tree
It
bubbling thing.
changes the
Okay, so cool. We know what affected us B then. Okay. Which of the statements about hash coding is true? If a dot hash code equals b dot hash code is true, then b dot equals a should be true. That's false, because you can have two things with the same hash code. If a dot b equals b is true, then a hash code equals b hash code should be true. Well, this is true, yeah.
That's true, yeah.
I'm going to post a message in the VC channel.
Yeah.
I just plugged it to the internet, so it could be false, but you know, it might be useful to have.
Hit me up. Okay. You understand this? Fail bubble sort, in place, stable, yes. Select sort, in place, stable, no. This seems quite interesting.
Yeah, you know, just another thing you can keep on your cheat sheet for
Yeah,
easy
you can
points.
just save all these images and download them.
Yeah, that's what I'm doing.
Yeah, it makes sense because like especially just have a folder with them.
Like
Like
I
you're
don't
allowed
know.
to make your own notes.
Yeah, this is technically not making our own notes, but we could have made this very easily.
Yeah,
I'm not
exactly.
sure.
Like we can just turn it into a table. Either that,
I
or we
think
can
this
take a
is still
screenshot of
technically
this,
fraud.
and then it will be our own made note. Like
I think this is still technically fraud, but like very, very much on the border of it.
What do you mean? It's an open book test.
Yeah, but the thing is, if you use your own notes, you have to make them yourself. This is not self-made notes, but they do not have a single way to see this. You know.
yeah, like I don't know what they qualify as self-made. Like if I make a screenshot of something, is it self-made? Because I make a
I
screenshot
think
of
if you
there.
take a screenshot of the lecture slides, it should be considered self-made because you're just taking the slides. And I think they allow anything that's in bright space. So any lectures screenshot should be fine.
Yeah,
but
but
this is not a
this
lecture
stuff is not in the
screenshot.
lecture. Like this is,
But like
this and this isn't.
this, like the last one you showed, the yellow one, is there like similar one is there in the lectures? Exactly like similar.
Fair, but for this one,
This one is not. So
It's also in the book, I think.
Well,
yeah, it's like
for the.
it is really like a really weird way of
countering fraud.
Yeah, this is like a more of like a moral question. Like
Yeah.
I could go into a text file and copy all of this. Would it help me in any way, shape, or form? Absolutely not.
I think for safety's sake, I'm just going to use the one that they made, and just look it up in the book if I need it. But
Yeah, that's true. I think I might like.
I get why people would use this.
Yeah, I think I might like try to copy this before the test into like my own notes. Or at the same time, like self-made is such a weird concept because I can make a screenshot and it's self-made.
Yeah, I think I think they mean self-deduced, but at the same time, things in the slide aren't self-deduced.
Yeah, it's such a really weird thing. Let's continue with our thing because time's ticking.
Yes.
I might actually ping my student mentor who's now on the server and ask her. But at the same time, we'll see. Consider the following fixed size hash table using linear probing. Associated values are omitted. The hash function is h of k equals to k plus 1 mod n. Assume we first insert an entry with key 27, and then delete an entry with key 26, and then insert an entry with key 6. In which bucket will the inserted entry disappear?
I just want to say,
sorry.
Sorry for wasting more time.
Insert an entry in key with key 27. So the hash code of 27 will be 28 mod 10 if it will be put in 8. Then it will pick the using linear probing, so it's gonna take the one that is, I think, closest to it, right? As in, like,
Just gonna walk to one, pretty sure.
Yeah.
but does
Does
it
it
go
go in a
to, like,
specified direction?
Yeah, it
or-
goes to the right and then circle.
Yeah, it goes. Yeah.
it always goes to the right?
Yeah.
Okay, cool.
I think.
So then it goes to the right twice or thrice. So then 27 gonna end up in 1. Then they delete key 16. So then space 8 gets freed up. And then insert an entry with key 6. 6 will be hash code 7. 7 modulo 10 is 7. So then it's gonna be put in bucket 8 again. If it only walks to the right, like you guys saying. So I think the answer should be D8. Haha, D8. It's like a D&D number. Dude, funny.
I got the one from the slides and put it in the VC channel, so you don't have to worry about the moral dilemma.
Yeah. And again, like, you can just go to
Thanks
the
for
lectures and make
relaying
copies of
it.
this. Okay. Consider the following AVL tree.
Just so you know, the answer to 17 is B and the answer to 18 is D. You missed one question. I mean, you answered it, but you missed it in the Watex. Yeah.
So it's like 17 B and 18.
Yeah, exactly.
Thank you. This would fuck me up on a real test, swear to God. Okay, not
You
really,
don't-
because it's in Brightspace
you
and you
don't
only
put it
can see
in,
the question sequentially, but still. Okay. Consider the following AVL tree. When deleting 40 from the given AVL tree, what was AVL again? The names of the makers, right?
Yeah.
Yep.
Ugh.
The very weird one. The
Yeah,
one
I
near
hate
the
when they have, like,
keyboard.
the names of the makers. Like, LSD sort is least significant digit. That makes sense. But then you have RSA, which is like the name of the guys who made it up, and I'm like, that doesn't help. Should have called it like modular encryption or some shit. Okay. When deleting 40 from the given AVL tree, how many trinode restructurings are caused in the tree? If that node is to be deleted or has two non-null children, the node will be replaced with an in-order predecessor, i.e. the maximal node of the left child. So when they delete 40, this one is gone. I'm gonna look up what an AVL tree is.
It says here, a get, put, or remove visits OH nodes and performs OH trinode restructuring. Oh, it's all OH.
Yeah.
Fuck. Sorry.
Yeah.
I can send you a
See,
screenshot of trinode restructuring. Oh yeah, you look them up.
Where is
That's better for the rest of you.
AVL?
Just look up.
It's a balanced binary.
Oh,
Isn't it in search
Wow.
tree or something?
An AVL tree is actually a tree that has a height balance property that actually says, hey, the left child does and the right child have a difference of maximum of 1.
Yeah, okay. For every internal
That's actually an
position
AVL.
P of T, the height of the children P differ by at most 1. Okay, so let's go here. So when this one gets removed, the height of this thing is 2 and the height of this one is 0. So this will cause 1 trinode restructuring, then 23 will become here, 20 will go there, and 30 will go there. However, then the height of this node is now 1, and the height of this node is 1, 2, 3. So then it will have to be restructured again, so it's either C or D. Ooh, that's kind of hard to do in your head. Holy shit.
Write it down then.
Okay, wait. I actually might. Let's do that.
Like you don't have to fill in the values in the trees, but actually you might. That's a lot work.
Okay, so we start out with a tree that looks
I mean,
like...
we only care about the subtree, right?
No,
Not
because
really,
you want
because
the
like the rest of the tree still has to conform to the AVL high balance property. Dude, I sound so technical right now.
I was about to say, I really feel like I'm in university right now.
So
just don't draw the bubbles.
I was about to say I'm just not gonna draw the bubbles. So we will start out with 19 here, 30 here, 40 here, 20 here, and 23 here. Okay, so when we remove 40, so when we remove this one, we will end up with this situation. And let me actually get an eraser real quick, or a pencil. However, this is not allowed because this thing has a height of 2, and this one has a height of 0. So they will get restructured. So then it will probably look a little something like this. So then we get 20 here, 30 here. And wait, that doesn't make sense, right?
I'm pretty sure 23 will take the place to 40. Doesn't it take the maximum child of the left subtree and place it in the place of the removed element?
But
Like,
if it
it
does
goes
that, then it
left
will
to
become
30.
23 here and 30 here, which is not allowed, right?
Yeah, but then it continues restructuring. I mean, I think that's the first step of the.
Oh, so you mean that this is like the first trinode restructuring?
Yeah, I'm not saying it's over. I just
Yeah.
think that's the initial state after the removal.
Okay, that's a good one.
And then it have to rebalance since it's okay.
Okay, then it rebalances. So then it does another trinode restructuring here.
Well, if there is a trinode restructuring, which is a double rotation, which fixes this.
Ooh.
I believe it is considered one restructuring.
Yes, a double rotation is considered one restructuring, so that
Okay,
will
so
be
then
two trinode
in this case there would
restructuring.
only be a singular restruction.
Yes.
Which would result in the tree we see here being
23, 20, and 30.
23, and 30, like this, right? That's not true.
Yes.
23, 20, and
Fine.
30.
Yeah, 23, 20, and 30. I was about to say, okay. So this looks good, but then this thing has a height here on the right of 1, 2. So 2, that's a really bad 2, and then we have 1, 2, 3, 4 here. So if this is seen as one trinode restructuring, let's see.
Actually, there is a question about what is considered as one trinode restructuring on Stack Overflow. I asked it, and I got a well answer.
Oh no, tell us about it. What's the answer?
Yeah. I can't explain it myself still, but it is a very good answer. So you should look it up in Stack Overflow.
I see. Well, that's not allowed on the test, so I'm not going to do that. But realistically speaking, let's see what. Actually, I'm going to look up the trinode restructuring thing, because maybe it's just in the book. Updating operations. Here, we rebrand the subtrees by calling the trinode restructuring method. There we go. Let's see. Yeah, okay. So h is height here. I was super confused about what the hell that meant. Okay, so rebalancing the subtree. A is before the insertion. B is after the insertion of subtree D3. Yeah. And then after that, it gets rebalanced. So the highest nodes will get put to the left.
If you just go to the next page.
I'm getting very confused. That's just because of like they use h plus 1 here as the height. What I was looking at it like h plus 1 and stuff being values. So I was getting very confused. But yeah.
If you go to the next page, it's talk. Yeah, this one.
Yeah. Is there anything about the double restructuring? No. Okay. I don't think there's anything about double restructuring of AVL trees in here. So
I sent you the link via Discord. I sent you the link via Discord to Stack Overflow.
Okay. Normally I would just answer, let's see, probably C to this question, but now we're going to look it up because I just want to be sure about this for the actual test. How is the single rotation, the double rotation, and trinode restructuring in the binary tree related? Recall a problem that a single rotation can solve. Okay. Problematic part to be in the middle. Single rotation over A all that would happen is this. It does not solve the problem. A trinode restructuring can be a single or a double rotation, and you use a single rotation if it's in the far left or far right, and a double rotation if it's in the middle. And we had a problem in the middle here because this was, or this one, or was it in the far right?
Can you put this link in the chat, please?
Yeah, sure. So yeah, here we have to do a double, but it does count about here. For questions about trinode restructurings, make sure not to count a double rotation as 2 restructurings. See example question 19 of this exam. That's like literally fucking what we're doing now. XD. Gag W. Okay.
So double rotation is 2 restructurings.
No, a double rotation is 1 restructuring.
Okay, that's what I thought. Good.
Okay. I think the answer is C then.
Yeah, I thought so as well.
Yeah, because you get rid of this one, you restructure this, and then you restructure like 10, 19, and 20. Or 10, 19, and 23 to make sure that the
Can't you just restructure the tree on the left?
This one.
Yeah.
But from this point onwards, nothing changes with the values.
Yeah, but you could probably still restructure it to give it a height that's 1 less.
Well, how? Because it's almost full. Like, I mean, you could try to put the 1 or
yeah.
so
If you
not
restructure these 3 numbers, like 8, 10, and 15, put 8 in the middle, 10 on the right, and 15 here down to the bottom, and then pull the 8 up here, the 3 up here, 1 here, 9 there. Then yes. So I guess that's what we could do. We could restructure 30.
Still 1 restructure.
Yeah,
so
exactly.
1 at the right, 1 at the left, still C.
Yeah, so it's still C. So 19 is C. Okay. Consider the following 2 for 3. I'm guessing we're almost getting to the end of the. Yep. Hell
22.
yeah.
There's 22 of them.
Yeah, and like this is something that is interesting because they go over the material in the same order that we get it in the thing. So
yeah.
They start out with like array list, singly linked list, and then they get graphs, and then they get trees, then they get graphs with sorting algorithms in the middle because I forgot them. When leading 3, 4 from the tree, how many underflows are caused in this tree? If the node is of the entry that is deleted has non-null children, the node will be replaced with the in-order predecessor, i.e. the maximum entry of the left child of the tree. Okay, so 34 is being deleted. So then this thing will have 0 values in it.
It gets
which is an
replaced
underflow.
By...
Okay, and then what? That gets. I'm tempted to say that gets fixed by a transfer by just transferring 80 to over here. Would that work though?
I'm gonna put up my notes and I'll tell you.
Yeah, my first guess would be B.
So
well, there are actually 2 underflows because first of all, 34 is getting lost, and that node is getting empty. Then it will be replaced by the in-order predecessor by 30. So 30 is going upwards, and then the node where 30 currently is as an underflow.
Oh yeah,
so I will think too.
You make a good point. We just didn't read the question right. At least I didn't. So if the node of the entry that has to be deleted has non-null children, the node will be replaced with the in-order predecessor. So that will be this one. So this will go to the left. And
the question is that an underflow? So
I think so. And then this is like this thing going here is a transfer. So it has 2 underflows. So this one gets deleted. This one goes there. That's a transfer. But then we still have an underflow because
30 has no value.
Yeah, because the 30 has no left child and it's a 2-4 tree. So there needs to be like between the 2 and 4 children, and now there's only 1. Is that correct what I'm saying?
Well, if you put 30 in the top tree,
in this one, yeah,
then this is difficult. So what would happen with the children of 30? So the left child would go to the left. What would happen with the right child? Would it be mended to the left side of 80? No,
I
there is
think
already.
these two children are 0, right? Or
No,
no?
they're values.
They know.
No, they
Or
know.
these no leaves.
Yeah, these are no leave.
Okay, then
Yeah.
I guess if you can just change them willy-nilly, then
Yeah, I think this one would go there. However,
well,
let's
thing is,
look it up.
I'm looking at the slides now, and every time they do a transfer or a fusion, the amount of leave nodes stays the same, and I've got a gut feeling that is something that is required. So I could be very wrong here, but
3 pages further is it? Oh,
yes.
1 page earlier.
1 page earlier.
2 pages further. I mean, it's
Good
almost
flex.
there. Now 1 page further. Down to insertion. 1 page further. That's deletion. Oh, 1 other page further.
Jesus Christ.
Yeah, here we are. Okay.
Okay.
Now the title deletion. Yes, and
Oh,
at the bottom of the page it says, to remedy an underflow, we check whether an immediate sibling of W is a 3-node or a 4-node. If we find such a sibling, then we perform a transfer, and else we perform a fusion.
Okay, that makes sense. So that means if we go here, then this is only a 2-node, right? Or
Yep.
Yeah.
Isn't that a 3-node?
No, actually it's a 3-node because it has 3 children.
Yeah, the amount of children. Yeah.
Yeah, so this is a 3-node.
Yeah.
Therefore, it becomes a transfer.
Yes, true.
Okay, so my gut feeling, or
2 underflows.
yeah,
2
which needs to be
transfers.
fixed by
B.
2 transfers.
Good.
Okay, dude, we're getting here.
Took us 20 minutes to do one question. Or
Shut
no,
up.
2 questions. Next, 21.
I mean, this one was harder than this one.
Yeah, definitely.
Okay, consider Kruskal
Kruskal!
Kruskal,
My favorite.
operating on a graph G is the collection of vertices and edges, where n is the absolute value of v. What?
The amount of vertices.
The amount of vertices. I was like, what? That doesn't make sense. But it's the yeah.
Where v is the number of vertices.
Where n? Oh yeah. Shut the fuck up. Which of the following statements is true? One needs an adaptable priority queue to pre-implement the algorithm. The edge with the highest weight, E, is never added to the tree by the algorithm. The union operation on partitions is called O min n of m times. And Kruskal algorithm starts with n clusters and terminates when there's 1 cluster left.
It's not B, because you can have a thing with 2 nodes and one edge.
Yeah, okay. That's fair.
It's
First,
just D.
let's recall. What is
Yeah,
Kruskal?
I think D is the simplest one, and it's also the one that you know is true. I think
Kruskal,
that's trivial.
quick explanation. Kruskal. So if you look at the thing below it, if you imagine you would Kruskal that, you would make all of them their own cluster, and then start merging clusters by looking at which cluster takes the lowest points to merge.
Okay,
or
that
takes
makes
the
sense.
lowest amount of vertex to merge. So
that makes sense.
Yeah, so it's D. It has to be.
Okay, we'll do D then.
Yeah, and it can't be C because in the example where I said, where you actually never mind, that doesn't make sense.
Yeah, and you can also use something else to implement the algorithm. An adaptable priority queue is nice, but it's not required.
We've done it actually on the implementation. We've done it without one. We used a union sum or whatever it's called.
Yeah, like a union set.
Okay, next.
In general, DAGs can have multiple topological orders. How many different topological orders does the above graph have? Honestly, I would just draw them out. I would just write them all out. So then there are, I think, 2 nodes that do not require anything, namely J and M. So these are the 2 possible starting nodes.
Yep.
After M, we can have N, and then either Q or L, and then we need J somewhere in between, and then we need K. So there are 6 nodes, so these are all the possibilities. Okay, so what are all the possibilities starting from M? Starting from M, we can then have J, then we can have N, then we can have Q, L, K. Starting from M, we can have J, we can have N, L, Q, K. Starting at M, we can have J, N. Are there any other possibilities for JN? Okay, Q. Okay, that's good. We can start at.
Like I could be wrong here, and I'm just checking. What is a topological order? Because wouldn't that also mean that J needs to be before K? And it can't be K needs to be before L because L needs to be before K. Never mind. Whatever.
Yep. So basically, for the people who don't know, again, a topological order is everything that is
in the graph is displayed.
Yeah, that and
the
like, for
directions are
example, you
followed.
cannot have K before M. That's the main thing. For something to be selected, all the the incoming edges of that
have to be selected.
Yeah, I'm not
Or
sure if incoming is the
already-
right word there, but you get the point.
Yeah, inbound.
So we cannot have K without L, M, and J.
Yuri, can I just real quick say something? I broke another game.
Stop breaking games. Leave.
No! No!
Okay, that's nice.
Their fault for having code vulnerabilities. We learned about this in security lecture.
We haven't watched
I didn't
it
even
yet.
watch that one yet.
This time I literally just sent a socket. I literally just sent the message "fuck you" over the socket, and that broke it.
Okay, but let's continue. We're on the timer.
Yeah. Kick W. Okay, so we can also start with J and then have all the other ones. So then we can have J. So these are just these three, but then swapping around M and J. And we can actually have J like almost anywhere in the graph. So can we
As
put
long
J
as
in another place? We can put J.
We can put J
after N.
everywhere before K, right?
Yeah, so we could put J here. We could put J here. We could put J. Oh, we could put J here.
It's really not shaping up to be 11.
No, not really. We can put J here. We can put J here. And we can put J here. Then we can. Oh. Then we can put J here. We can put J here. However, we cannot put it here because if we put it here, then it's after K. So now we will recompile so you guys can actually see what the fuck I'm doing, and it will show up. Oh, at least decent. Wow.
Decent.
Okay. I didn't expect it to look that well. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. My answer so far would be 14. However, I'm not sure if this is the total one, so I will proceed to look at the graph for a little while longer. Well, N needs to be behind M. And N has to be directly behind M, with the only exception being J has to be in between that. So MN has to be in that order. That makes sense. Then we can pick either Q or L, but we already swapped those around over here. And we can pick K after L if that has already been done. So is there any other way to change these last three nodes? We cannot put K any further before L. We already have Q, L, K. I am pretty sure.
Everything with J is already done. Everything with J at the start.
Yeah, everything with J at the start is already done, I think. I think the answer is 14 then. This is of course not the best method because you can like definitely forget something. But
it is definitely possible to check, and it would take you like 5 minutes max because there's a lot of seconds in a minute.
That's true.
By the way, are we sure about 21?
Hmm?
Why can't it be C? Why is C wrong?
But we just know it's D is correct. We're not sure. We haven't checked the rest.
No, because I think D is not necessarily correct. Like if the graph isn't fully connected, then you might end up with more than one cluster.
That is true.
Yeah.
That is true. You make a valid point.
Because a graph could just be a forest.
Yeah, a graph can just be two trees with only 2 nodes with 0 edges.
Yeah.
So there might be more than one cluster left. That's a good call. So looking at that one, I'm gonna remove these. Looking at that one, which one did you think was correct?
C.
Probably C.
It looks like C.
Yeah, it can't be B. It can't be A.
Yeah,
so it's either C or D. So if we don't forget about the fact that there's a forest, it's indeed C.
Yeah.
Nice.
The edge with the highest weight E is never called to the algorithm. What if you have two things that are connected and it just has like the highest height inherently? So B is always false, and you do not necessarily need it adaptable priority queue. So we need it probably C. Okay, that means we are done with the multiple choice questions. Oh no. So now we have the open questions. How many are there? 1, 2,
3.
There's genuinely only 3 questions, but there are sub questions. Okay, that's fair. Okay. Consider the following Java implementation of the following method X. Public static int method X takes a graph of an integer. Take a graph with. Oh yeah, okay. A graph which has.
Integer.
Yeah, but I'm trying to figure out what these are.
Vertex edge.
Vertex edge.
Maybe.
Okay, that makes sense.
Maybe.
Perhaps. Oh.
We'll see.
Oh yeah, okay, and that graph's called G. Int X is G. So it creates an iterable out of the list of vertices of G. Then it goes through the list of vertices. Then it gets all the edges.
From that vertex.
Yeah, so this just sums the entirety of the graph.
Yeah.
Or
it sums it twice, because is it directional or not?
Let's read the question.
Sure.
Assume that graph G is implemented using an edge list data structure and does not have parallel edges or self loops. Give the polynomial expressing the tightest worst case time complexity of method X as a function of the numbers of vertices n, numbers of edges m, and degree v of a vertex v is part of v of the list of vertices or the set of vertices of graph G. Define all variable and constants. Explains what lines of code contribute to each term of the polynomial. I understand why this is 5 points. Okay, so looking at 23. Assume it's implemented using an edge list data structure. I think you actually sent a screenshot somewhere in the.
I can give it to you again. So there's graph data structures, asymptotic performance.
Okay, wait.
Copy.
Here it is.
Oh, you got it already.
Yeah. So these are all the functions that we know exist. So all of them. So the only things we care about here is we call outgoing edges here. This is just a for loop. This is just addition, that's constant time. Get elements, constant time. Yeah, I think this is just okay. Yeah, I think that's all we needed. That the fact that outgoing edges is in an edge list here, we can see outgoing edges is big O of M. So we can start working. So from top to bottom, we have line 1 constant time. Line 2. Well, that just creates an iterable, so an iterator from the list of vertices. So we can assume that's constant time as well.
For the record, that's not an iterator. It's just like an iterable. So like it could be a linked list or something.
Yeah. Okay.
Yeah.
I don't exactly know how iterator iterable how that works, but I know that like creating it is.
All that matters is that it is something that is that is iterable, and it is a subclass of iterable, so therefore it has to be iterable.
Yeah.
Can you check the VS channel to see what I sent you?
Yep, sure.
If it is correct. It is for question 21.
Okay. So he says this is for question 21, right?
Yeah.
Implemented using a priority queue that stores the edges outside clusters. The thing is,
it seems like it doesn't care if it's outside the clusters. And in the end, we should only have one cluster.
Well, I think if you call this on, on a tree or a graph with a single tree, then you'll get the right thing. But you can't get a single cluster if you've got a forest. So I think this ID thing isn't concrete yet. It isn't doesn't list edge cases like multiple graphs. Because if you have a forest, it will never get a single cluster.
Yeah.
Okay.
Because there's no edge between them.
And it's implemented. It can be implemented using a priority queue. I would say.
Yeah, it doesn't have to be implemented using a priority queue. But
But
thanks
it
for the
can.
reaction.
Yeah.
Okay. Yeah.
This is good. This
No.
sparks discussion. Okay, so line 1 is constant time, line 2 is constant. Oh wait, let's use the actual line numbers. Line 2 is constant time, line 3 is constant time. Line 4, everything in here happens, and that happens the amount of vertices times. So that is, let's see, so that's number of vertices n. So everything in here happens n times. So then I'll indent it, line 5. Outgoing edges v is of size, is of time m. Calling outgoing edges with a edge list is big O of m. So therefore, let's see, is it, yeah, okay, cool. Then line 6, everything in here happens. Okay, so that's the amount of edges for said vertex.
Yeah, degree is that.
Yeah, the degree v of a vertex v. So that will be everything in here happens deg v times.
Isn't that equal to n?
Well, the degree of a the amount of edges of a vertex and the amount of edges in the graph are two different things. Or and the amount of vertices in the graph are two different things.
Yeah, but we're calling we're making an iterable of the outgoing edges of v, and then we iterate over said edges, right? Oh, okay. No, I see what you mean. Yeah, I'm confused. Yeah, I get it now.
Okay, line 7, that takes constant time. Is that correct? Well, yeah, there's no like axis here, but I think that would just be constant time because it's used with a link with a list. So therefore we have the time of S is C2, so the constant time that line 2 takes, plus C3, the constant time that C3 takes, plus n times, let's say m, because of line 5, and then plus degree of v times constant 7. I'll call it C7 just because it's the constant of line 7. So we have C2 plus C3 plus n times m plus the degree of v times C7. If we get this this out of the brackets,
Is it just degree of v or the sum of all degrees of v?
well, it's n times the degree of v.
But
and where n are all the v's.
No, but then you would write that differently. Then you would write the sum of all v degrees of v for all v's, which equals to n. Or to m, one of the two.
Yeah, okay, because it happens m degree v time.
So wait,
so I'll take...
does deg v get called for the entire for every vertex?
Realistic.
Yeah. So once you expand the brackets, that's when you get like the sum of.
Okay, because v is not technically a thing you can write in here, I think, because you don't know which v you're talking about. You're not defining a v.
Yeah, I think that was the thing in the book.
Well, I mean, it says
that the
as a
sum of
function
all of
of.
the outgoing edges is 2m.
Yeah, but
You can have a
it says
subscript
it
that
tells
says
us to
like-
make it as a function of degree v.
Yeah, you
You-
can.
You can
This
say,
should
like,
be
degree
fine,
of
I think.
v subscript n, and then once you expand the brackets, you get like.
Yeah, so I'll call this degree v of n.
I would put the subscript next to the v, but that's me.
Yeah, like
Yeah,
inside the
okay,
bracket.
that's fair. Of n times this. So then what we would get is t of s equals constant constant of line 2, constant of line 3, plus n times m plus the degree of the amount of vertices of n times a constant. Well, I'll say call c. I'll just use a number that I haven't used before. I know that gets confusing really quickly, but whatever. Plus c4 c2 plus c3. Therefore, copy this. Oh, I put a bracket in the wrong sign of the thing. So then we only have one constant here. ds is c4 plus n times m plus n times degree v of n. I'll use c dots here. Oh, c dot v degrees n times a constant. So if we compile this, you will see that therefore ts is c4 plus. Oh, I accidentally pressed my insert key. So it is n times m plus n times the degree of vn. And you said it was in the book somewhere that is that is 2n.
The sum of all degrees is twice the amount of vertices. Actually, is that always the case?
Yeah, I was about to say I want to see that in the book real quick then.
It's twice the amount of vertices, yeah, because every vertex is counted twice, has to be.
Yeah, that
So not the
sounds
amount of
right.
nodes, but the amount of vertices. Because a vertex connects two edges, and for if you count all the degrees for every edge, you get every vertex twice.
Yeah, okay. It makes sense. I wanted to see it in the book, but like it does just make sense, so we might as well just use that.
Yeah.
So n times the degree of vertices of n. For all n, it's just equal to 2n then.
Yeah.
Okay, then recompile.
Is that 2n or 2m? Sorry.
N.
2n.
The amount of edges. Or
it's
edges.
going to be 2m.
No, n is vertices.
Yeah, we want edges.
Okay, so it's 2m then. Okay, yeah.
Because every edge gets counted twice.
M and blah blah blah.
Yeah.
Okay. So we have c4 plus m plus 2m c to the power 7. Well, I guess that, and from that point onwards, we can just say that the biggest growing factor of that is equal to n times m for all n bigger than 2. So this would be big O of n times
Well,
m.
they don't want the big O yet, I believe. They want the polynomial.
Yeah, okay. This is the polynomial. So this is well, actually, we can say call
2 times c7.
c7 is equal
C8.
to c5. We haven't used that one yet.
What?
I'm just go. I first labeled them by line numbers, and then I stopped labeling them by line numbers. T of s is equal to, or this should not be T of s, by the way. This should be T of n, comma degree of
v
of n. Actually, they ask us to give it like this. We'll just do it like this, whatever. And also v n times degree of the amount of vertices of n is equal to 2m.
Yeah, if they say give it in deg v, then I guess you don't have to write the subscript n. But as long as you know that when you do it for every vertex, you can use that. I think that's the most important one. You remember
Therefore, n t dot m, well, we call it t5, so this is t of n comma m comma degree of v. Therefore, t of n comma m comma degree of v is equal to c4 plus n c dot m plus m c dot c5. Okay. So big T of n m degrees v is c4 plus n m times. I'll turn these two around so you'll get c5 c dot m. Recompile. So this is our final thing. If the graph G was implemented using an adjacently list data structure, what would the tightest worst case time complexity of method X be in big O notation? You do not need to write a polynomial nor give a proof, but you should motivate your answer. 24. For all m
I would say right for all m greater than 2. It is important.
Yeah, okay. For all m greater than 2, the biggest or the fastest increasing term in that polynomial is n c dot m. Therefore, it is big O of n c dot m. What I'm saying is not correct. It's for n bigger than. Well, at the same time.
Actually, I don't think it matters too
Yeah, I don't think it
much.
matters at all because there's also
Yeah,
constant here.
we merged it with the constant. Yeah.
Yeah.
Sorry.
Okay, for all the fastest increasing term in that polynomial is n c dot m. Therefore, it is big O of n c dot m.
Yeah, I mean that's all. I don't know if this is enough explanation, but it seems solid.
Yeah, I don't know what else I should say.
And this isn't 24. This is 23b.
Oh yeah, good call. 23b.
Everyone still awake?
No.
I don't feel like it.
I feel like that, but no.
Okay, we've lost half our people. That explains why it's so quiet.
Yeah. Near the end of the test, it always becomes way quieter.
This is like half the test, so this is one of the most important bits.
Yeah, it is. Like this stuff. This is like the most important stuff.
Yeah. This is also the part where I got a fucking 3. I got a 7 on the other half.
Yeah. You should explain, but you don't need to give a proof. Okay. If the graph G was implemented using an adjacent list data structure, what would be the tightest worst case time complexity? Method X in big O. Wait, that.
It's basically what changes if, like, just look at the big O notations for the adjacency list. And compare it.
Oh, an adjacency list. I thought it said edge list again. Okay, cool. So we will proceed to do that. 23c. So if we pull up this one, an adjacency list, the outgoing edges is a degree of v. The outgoing edges of what? Of v is a deg v in an adjacency list. Therefore, the polynomial would be, and they say you don't need to write it down, but I think it's easier that way.
Mm-hmm.
So we have this is the original polynomial, and let's see, outgoing edges in our thing with OM, and now in the new thing it will be O degree of v, deg v, which would be which would equate to this is, what do we call it, constant? C4. So we have C4 plus 2n, or let's just say like a next constant C6 and degree V.
And deg V. Oh.
Hmm?
Can you do that?
Well, if we just say.
Oh yeah, because it's 2 and 2 deg V, and 2 is a constant.
Yeah. Well, let's see. If we work this out, so we started out with this, then
Yeah.
it will be.
C
oh yeah,
C7
okay. So
plus
we can
1.
we can expand this to be deg V1 plus C7.
Yeah.
Like this.
With a bracket.
Yeah.
Sorry, where did the 2 come from?
The 2 is already there.
Was it though? I think you just added it.
Wait, was it not?
And if not, it doesn't matter.
Yeah, no, I see. So it was n deg V. I didn't. Yeah, okay, cool. Excusez-moi, but that means we can call 1 plus 1 plus C7. We can call that, I don't know, C8 or something. I don't fucking know. I need help, man. So C8 is 1 plus C7 gives this time complexity is equal to C8 and degree of V. And since we know that n times degree of V is equal to 2m, we can add that to our function as well, and therefore that will turn it into 2m, which is big O of m. Okay, let's see if we spot any mistakes. So that's not pretty. Okay, the outgoing edge V is deg V in the JC list, therefore the polynomial would be t is this plus this plus this plus this, which would equate to, well, let's see, 4 that we knew that. We turn it into 1 plus C7. I think we just copied it here, so that line can go away. Yeah, this line. And therefore we get that it is C4 times C8 times 2m, which is big O of m. Okay.
Okay, wait, sorry.
2 more
I have
questions.
one question.
Ask it.
When we were doing like part A,
yeah,
we were making the polynomial, right?
Yeah.
All we have is the big O notations of like outgoing edges and stuff. So
yeah.
how can we just use m then in the polynomial, because then
Okay,
that doesn't
you do make a good point. So because it is big O of v, we should theoretically actually do like a constant times m, I guess.
Yeah, but it could also be a constant times m plus another constant, or plus like n or
True,
something.
but that won't matter if we just want the tightest bound. So even if there are more less important things behind big O of m, they will all fall away when we eventually take the final big O. I do agree that it's
Yeah,
like
when we do, but then the polynomial isn't complete for part A exclusively.
I'm not sure if there will be.
But 23C doesn't need a polynomial.
Hmm?
But if it's different,
Yeah,
if we're talking about the original polynomial, then you need to change it.
Yeah, so that would be this one. Then we'd have to say that it is OM. Therefore, we have, let's say, C 10 times M, whatever, and then there we would also have to carry that through to everything else. But in the end, our thing will still be big O of
Yeah, so the big O's won't change, but
yeah, but we would have to carry that over. So, yeah, I can do that real quick. Okay, we're done. Because here I just say 2 C7, C10 is C5, and then everything else will just continue like normal.
Only took us half an hour.
Sure. Yeah.
Yeah. Okay. Then we have 24. I mean, realistically, on like a test.
We're at the third. Woo!
Yeah, realistically on a test, we would still have like a full hour or like 15 minutes, which is, I think, doable. Yeah. Okay. 24A. So we have method y. If n is 0, if n, then it's 0. If n is y, it returns the data of I, and then this calls. Okay, the first thing is always the data thing. We don't need to look at that. I think this is just a very exhaustive sum method. So let's see.
Yeah.
Yeah, it's just it adds all the numbers from 0 to the end, then it splits it up with the divide and conquer method from so like in the first half plus the second half, and then from that first half, second half until it's either 0 or 1. So I think this is just one big sum method. State the base and recurrence equations for the space complexity of the recursive method. Clearly state what you consider to be the input size and refer to the relevant part of the code to justify where your equation is correct. Okay, so I will do the same as first. So line 2, constant time, constant space. Line 3, constant space. Do we need to do the time complexity anywhere? I don't think so, except for like describing an improved method.
That's also in terms of space, I think. So, I think we improve it in terms of space complexity. We don't really have to care about time.
And same big O worst case time complexity.
Oh wait, okay, never mind.
Yeah, no worries. Line 3.
Do 2 and 3 even use any space?
Not at all. But 0 is a constant.
I guess.
Yeah, like maybe they would use space for like the data element, but all in all, it's nothing significant. I'm not sure if they'll get marked down. Probably not. 4 is S of. So I'm gonna explicitly say here, the input is the amount of elements to consider, e.g. n minus I. Is that true? Yeah, because at first the amount of elements is 0 minus the length of the data. The length of the data minus 0. So that's like the total amount of elements, and here that will be cut in half, and this will be cut in half here as well. That makes sense. And this will be S.
I think this method does something else. Like if we try just plugging in 0 and n, then like the first recursive call is gonna be 0 to n divided by 2. The second one's is gonna be n divided by 2, n divided by 2.
Yeah, and also the first one doesn't do I, comma, n or I. Well, it does I n divided by 2, but it only does it from like the final thing it gets.
Yeah, I do agree. I misread it. I thought it said n here.
No, yeah, and the fact that it's I plus n divided by 2 also doesn't make sense for the last one, because if n will be the total thing, the total size, then I plus n divided by 2 is going to be something else than what you want it to be.
Would it be? Would it not be half?
Well, so imagine if you give I to n to the function,
What?
then or no.
I mean, in this case, we're always using 0, aren't we?
I would say let's write out what the function does for a few seconds.
Sure. Let's
Yeah,
have a
yeah,
look
yeah.
at that. So I will add a few new lines here. Recompile. Okay. So imagine we have the list 1, 2, 3, 4. So in that case, it will be method y data 0, 4. That will return method y. I'm just gonna get rid of the data thing because we know that it's gonna be data.
Yeah.
Method y of I, that's 0, n divided by 2 is 2, plus method y, and this is I plus n divided by 2, so that's 2, comma, n minus n divided by 2. Well, that's 4 minus 2, that's still 2. Then it's going to return method y. So it's from 0 to 2. Well, n is 2, so it's still going to continue. So then it's going to go from 0 to 1. I'm going to put brackets around it to indicate the order. Then we have method y 0, 2. 0 plus 1, 2 minus 1. So that's just going to be the same thing again. And then it's going to be plus method y, and this is 2 plus, let's see, so n is still 2, so we're not going to do any of the base cases. And this is going to be from I, so from 2 to n divided by 2. So that's from 2, one element. And then the second thing is plus method y. Well, it starts at I plus n divided by 2, so it starts at 3. And it ends up with 2 minus 2 divided by... Well, this is just a distraction. We can just call this n divided by 2, right?
Yeah.
Okay, so that's just going to be 1 as well. Okay, so this is going to return method y 0, 1. Well, that's just going to return the 0th element, so it's going to be 1 plus, and this is going to return the... It's going to return the second element, or the...
Yeah.
No, because it's going to be 2 and not, well, the thing's 0 based. So it's going to return the third element.
Yeah.
Oh, yeah.
So it's going to be 3 plus 4. That is so weird. Why would you create a function like this? I didn't make a mistake anywhere, did I?
Oh, wait, isn't the second one supposed to be 1, 1?
Yeah, I was about to say, that doesn't make sense. So it's going to be I times, yeah, okay. Then it makes sense. Then I think it's indeed just a sum function.
It's written so weirdly.
Yeah, holy shit.
Yeah, but if you look at it, it's more space efficient.
Yeah.
What?
So, yeah, this is just n divided by 2 then. And I think in that case n is just the amount of... Oh, yeah.
Actually, no, that might be wrong. It's just weird. It's not
Yeah, the
even
second thing given with is the amount of space slots you have left. That's actually really useful.
Yeah.
But it's the fact that
n
it's
minus
n
I,
minus.
that should just be n. And we do not need to call it xn.
Yeah.
Okay.
They kind of threw us off with the n minus n divided by 2.
Yeah, I was really confused there.
Also, commenting people, Jesus.
They say we have to comment and then they give us this shit? Jesus. Okay, So it's I. Well, the I thing doesn't matter. The only thing that matters is, yeah, this is just s of n divided by 2 plus s of n divided by 2. Yeah, so all in all, therefore s of n equals c1 plus 2 s of n divided by 2. How they fucking threw us off with one single simplification. Holy shit. I'm gonna add a comment here because the n becomes n dot 2 n divided by 2 in the first half, and n minus n divided by 2 equals n divided by 2 in the second half. And I'm gonna do it in the neat way. So I'm not gonna say n slash 2, I'm gonna say frac n 2 and n minus frac n 2 equals frac n 2. I paid for the latex, I'm gonna use the latex. Okay. So then we have, oh. Yeah. So then it becomes big S of n over 2 plus big S of n over 2. I like how I'm calling it big at this point, even though it shouldn't be called like that, but whatever. Big complexity.
Big,
The big,
big
ass.
ass.
Okay.
The time's getting to all of us.
Yep. And refer to relevant parts of the code to justify whether your equation is correct. Okay, then we go to 24b.
Base case. S of 1 is equal to C0.
Oh yeah, and the base case, that's a good one. Also on line 2, we are given a base case s of 0 equals c. Okay, that's constant time, let's call it c2. Also on line 3, we are given base case s of 1 is equal to c3. Would those be called like C2 and C3? I'm not sure if they take any space, but you know, I'm rather safe than sorry.
At either rate, it's going to take the base case is going to take some space just because of the frame for the
Yeah, okay,
function.
because it needs like the frame indeed.
Yeah.
Okay. B. Derive the closed form for your recurrence equation by repeatedly unfolding it. Okay. Then we get S of n is equal to C of 1 plus 2 opening bracket C of 1 plus 2S of n frac n over 4. I'm gonna turn this into frac n over 2. Folding this out gives 3c1 plus 4s n over 4. Then we get 4c1 plus 2s frac n over 8, which will unfold. I think I added a bracket too many here. Yep. Which will unfold to 7c1 plus 8s n over 8.
Why do you have a constant before C1? Why does it grow larger?
Hmm?
Because it doesn't say n C1, so I'm kind of confused as to why it grows with 2.
Because we do 2 times s of this thing, and s of this thing is just equal to
Okay, I see
c1
it
plus
now.
blah 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 blah.
Okay, yeah.
Yeah, and then we just get it out of bracket. Then we can say after k steps, we will get, and I'm gonna use the double things now because I'm fancy. S of n equals to the sum of from I equals to 0 to k, because we've done k steps. Either that or it's k minus 1, because at the first time we will have 0. Oh no, I think that's fine. When you have a sum from 0 to 0, you just plug in 0, right? Yeah, I think so.
Yes.
And then you just have 2 to the power of I plus, and then we have 2 divided by k. Well, in the after the first step, we have done 0 things yet, but it is 2 already, so it's gonna be 2. It's to the power of k plus 1. And then times s of fraction n divided by 2 to the power k plus 1. Okay, now we're going to check if this is correct. Oh, this doesn't look right. Sum from I... Oh, sum from I is 0, so I should have added brackets there. Yeah, so we have the sum from I is 0 to k after k steps of 2 to the power I. So after 0 steps, we get just 2 to the power 0 is 1. Then we have plus 2 to the power k plus 1, because after 0 steps that's just 1, so that's 2. And then we get n divided by 2 to the power k plus 1. And after 0 steps, that's just 2. I think this closed form is correct.
Can you go a bit to the left?
Yep.
Shouldn't it be the sum of something something times C1?
Oh yeah, it's 2 to the power I times C1. I forgot that one. Thank you.
Big brain, you.
Big brain,
You know what we should do somewhere in the weekend? Both make an exam ourselves without having other people to help us, because just to see how prepared we are.
Yeah. But yeah, I think this is correct then.
Yeah.
However,
Are
we
you
know
still
that
supposed
the
to?
sum of all 2 to the power I from 0 to k, well, we already know what that is. Namely, that's like the same as saying putting the first k bits on. That's the same as saying 2 to the power k plus 1 minus 1. 2 to the power of k plus 1 minus 1 times c. Okay. Do you guys understand that step?
Yeah,
I do.
Okay, cool.
It's just a geometric series.
Yeah, exactly. Okay, we cannot simplify this any further. This looks good. So then we would say we want to end up at s to the power of fraction of n divided by 2 to the power k plus 1 is equal to s0. Is that a right thing to say? Let's just get rid of the s because they might get angry at that.
Yeah.
So we want to end up at s of 0, that is after so many steps. And we want to express this in terms of k. So, or we want to express k in terms of n using this equation. So we're going to multiply everything by the bottom half. Then we'll get n is equal to this thing.
Wait, that's not true. If you multiply everything by the bottom half, you get 0.
Excuse me, we can take a base case of n equals to 1, that's fine.
Yeah. Well, the base case is n equals to 1, if you look at it.
Yeah, well, I mean, we can have two base cases, n equals 1 and n equal to 0. But, yeah. Then we get n is equal to this thing, then we take the 2 log on both sides, so then we get log 2 of n is equal to k plus 1.
But I think the first base case is there to throw you off, because I don't think it ever gets run.
Yeah, I think that actually might be true.
Actually, it might be if your first I is 0. Yeah, I think it's only then.
So then we end up with k being equal to 2 log n of minus 1. K is equal to 2 log n minus 1. Filling this in our equation gives us...
Which is very nice, because a lot of the time we use k, it's k plus 1, so it's just 2 log of n.
exactly. I think it's actually all the time.
Hey.
Yeah. That's why, like, you can take k to be, like, 1 based, and you will get the same answer.
Yeah.
It will just get rid of the plus 1, minus 1 everywhere. So
Oh.
I will fill in this, and then fill in this instead of k. Oh, shit. Shouldn't have pressed insert there. Okay. So then we can take this away. Then this becomes 2 to the power 2 log n. That becomes n. Then we get n divided by n. Well, that's just 1. Then this becomes 2 to the power of 2 log n. So this just becomes n. And then this becomes 2 to the power of 2 log n minus 1 plus 1. Well, that just becomes n minus 1.
N minus 1 times c1.
Yep. And well, we've already said that that S1 is equal to C3. So we can just say this is equal to C3. And this becomes n times C minus 1 times n minus C1 plus this thing. Well, then we can factor an n out of here. And then we get negative C1 plus n times C1 plus C3. Then we can say, okay, we will use say C4 is equal to C1 plus C3. Then we can have just a constant times n. Okay, then we have the closed that is the closed form, and then we will get to 24.c. State the tightest worst case space complexity method of the method in big O notation. You should clearly justify your answer. And then we can just say the fastest growing term is n C4, so it is big O of n.
That's a strange question. That's so simple, and it's worth 2 points.
Yeah.
It makes me suspicious.
Yeah, it is, but like people do not. If you do not understand big O, then you cannot answer that question. So. Describe an improved version of method Y which performs the same calculation as method I with better big O worst case space complexity and the same big O worst case time complexity. Give the big O space complexity of your improved solution. 24.
Perhaps by not using the double recursion. Maybe by not using the double recursion.
By making it tail recursive.
Yeah.
Private static. I'm just gonna program in my fucking exam. I don't care.
Describe here.
My sum int data int I equals 0 for int, or let's say int sum is 0, int I is equal to 0, I less than data upon length I plus plus. Sum plus is data I. While this is still big O of n time complexity, the space complexity goes down to big O of 1. Because you don't create any new space other than like the one stack frame.
Yeah, and some, but
yeah, and some extra for
some
like the integer I and the integer sum and other stuff. But all in all, it's still constant. I put a fucking punt comma at the end of my line. Okay, so I'm gonna add new lines. It's probably gonna complain about some stuff because it doesn't like being coded in. I'm not sure if this would even get you full points, honestly, because they say describe.
You also don't have a return statement.
Yeah, you might want to return some
Oh,
at the end.
yeah, that's a good one. Return some. And then I have to escape my backslashes.
Oh yeah, never mind.
It doesn't let me fucking do this shit. Holy hell, this is tilting. I mean,
Then just
realistically
don't-
speaking,
Like normally you wouldn't use LaTeX here. You would just
Yeah.
like throw it in bright space.
yeah, not only that, but you can just say this is like valid code as well without any any braces. Done though. I think for the rest is still correct. Except for like this thing, but that's just because this I
Oh
should.
well,
This
it
is,
works.
There we go.
Okay, nice. Is that all of 23?
I think
And
so.
we're still on pace for finishing in time, which is
Neat.
you know.
That's
Which is
all
like
24.
surprising.
So now 25 left.
Oh, A is easy. Yeah, A is easy because they told us how to do this in a lecture which you weren't at. So I'm gonna send you the screen of how to do it.
Okay, cool. I like how it's an open question to list the properties of AVL trees in an open book test.
Oh yeah,
Copy.
we just
I mean, then again, this test was not open book last year, I guess.
Yeah.
General
yeah.
VC. Send.
You were only allowed to have a self-made cheat sheet onto this test.
Yeah. Okay. Give a red. Well, give a red black tree that corresponds to the given 2-4 tree. The thing is, we'd have to draw this. I'm just gonna draw it on here, and we'll see like how it goes. So actually, gonna delete it all. So we currently have it like this, then this, then this, and this, then this, then this, then this, then this. For the people at home, to do this, you'll send this screenshot of the lecture.
Yeah, and how many trees are there? 2, because there's one with 2 which you can transform into 2 ways.
Yeah. So we have we start with this. Then the left side becomes more complex. The right side becomes more complex. Left side stays generally the same. And then we get this tree thing that becomes like this three-way thing we can split up in this thing here. Oh no! It closed everything. No, the horror.
Yeah, like fuck that small little half a millimeter thing at the bottom right of your screen, which if you click it closes all your tabs.
Yeah, fuck that shit. Honestly, who even invented
Can't
that?
you just
Who?
do super D and then cancel it, undo it?
Probably.
Very possibly.
I do not know. But then we get well, from there on we get this one to the 1511, this one to the 25, and this one to the 35, this one to the 80.
And
this
the bottom
one,
one, yeah,
and
split
this one can turn into either so either this one or one where we swap those two around.
Yeah.
So I'm gonna turn this one to red and this one to black. So let's see, any singular node turns into black. Any singular node turns into black. Is this correct then? So the left side, at least?
Yep, seems like it.
Okay, and then the right side we have a three big things. So now we can turn this red, red, red. And then this becomes black.
Black, and then the one below it comes red, yeah.
Okay, so this would be the tree that I would give.
Yeah.
Okay, and then we say
looking good.
This is question 25A. 25A. Okay.
// box.
25V.
Two.
There are two trees because the.
Wait, do you have to explain it?
Yeah, it says
Oh yeah,
explain.
explain. Sorry.
Because the 15, 17 can have the 17 on the left or on the right of the 15. Yeah, if you have a look at the amount of people we have left, this is usually how it ends, with about half or a quarter of the people we used to start with.
We the real OGs though.
Everybody at the end of this, or even better at the end of like a 7-hour lecture, those are real OGs. List the properties of AVL trees.
Control F.
Trees. Yeah, sure. AVL.
Sorry, Jura. Like, but it's like watching your fucking grandmother open up Google and type in google.com and then press enter and go to Google to
I don't
Google
know.
something.
For me, it didn't work, and I didn't understand why. It gave like really weird results.
For me, it's always worked.
Okay, fair. Maybe I was using something else to open PDF with or whatever. I don't
Very
fucking know.
possible. In Chrome, it's not as optimal, I must admit.
Yeah, I think I was using Chrome then.
Well, I've seen
List the
people
properties
type in internet into Google
Yeah.
to get to the internet.
Yeah, something like that.
Yeah.
That's beautiful.
Then we say 25C.
C.
AVL trees have a, and then we just copy paste it. Tres af.
It was 3 words. You fucked up 2 of them.
Correct. Is every red black tree also an AVL tree?
Hold on. Now, list the property of AVL trees. You've listed one, but you should also probably
and
say
it is
that they are trees and stuff. You know.
A multi-way search tree, and that recursively says it's also a tree and a etc.
Exactly. That's one you shouldn't forget. That's why there's 2 points probably.
Yeah, and then for
25D.
25D, is every red black tree also an AVL tree? No, because they can differ more height by more than 1, I guess. Oh no, what?
It is if you transform it.
Yeah, but was that the question though? 1, 2, 3, 1, 2, 3, 4. Ours is.
Look what I sent you. Every tree can be transformed.
Yeah.
Because you can just do it the other way around.
Yeah, okay. But if no,
you can turn.
They're asking, is every red black tree also an AVL tree? Like they know they can transform it, but if you have a red black tree, is it per definition an AVL tree?
Transformation. It's a different way of writing.
Yeah, but if you write a red black tree in a different way, it's already a different tree. So
yeah,
it's the same tree.
It's not like it's a transformation where you move around nodes.
It is.
I guess if you're going to look at it from there, and strictly consider a red black tree an AVL tree, then no.
Okay, let's see. Explain why properties of AVL tree hold for every red black tree, and if you answer no, give a red black tree as a counterexample and explain which properties of the AVL tree does not hold.
Yeah, okay. They do, if I read that question, and give a red black tree
then we need
as a counterexample.
We need to try to create a red black tree that does not hold the height thing property. So
this one, the one you just made.
No, this one has 3 and this one has 4. So, oh wait, no, this one has like 1, 2, 3, 4, and this one has 1.
Yeah, and at the left side there's 2, so it violates it like almost everywhere.
The no, comma the one I just made. Cool emoji.
Nice.
Righty ho.
Righty ho, and that is time. Still 18 minutes left, even though I will probably in the actual exam take a lot longer because I had you guys to help me.
Plus, usually it would take the last time to just check everything.
Yeah. Actually,
Isn't this 2 hours and a half?
I thought it wasn't. And if so,
I thought it was.
Yeah.
and if it is, like for a long time, we've just been arguing for.
Yeah, usually we argue a lot. Like the time you spend here is not like it's not relatable to the time you would spend in an actual exam.
We've actually been arguing about stuff that wasn't related to the exam at all.
Yeah, exactly. That is
for like at least 15 to 20 minutes.
And the morality of fraud and shit.
Yeah.
Yeah. Okay, so exam answers. Okay. So starting from the top, I'm gonna start with. I'm gonna start like. I'm gonna add a 1 if it's true and a 0 if it's wrong.
Very computer science like that.
Yeah. The function n log n grows faster than n when n grows
Yeah,
arbitrarily
we had
fast.
that one
Yeah,
correct.
we had that. Okay, then we had
You should
C.
probably close those side windows.
Yeah, good point.
Yeah, that's
Which of the
gonna save
following
you
is
some.
wrong? Yeah.
Just since we've already discussed the ones that are true, just I would say only go over the ones where we have it wrong.
True. Okay, we have that one correct. We have.
Wait, are they all correct?
No, A and B are correct.
Oh, sorry. I thought they all looked correct. Thick lines.
Okay.
D
D
is
is correct because it's exponential. Method. Yeah, that's correct.
Correct.
This involves the result of an. Which is
Yeah,
not.
amortized, which is not probabilistic. Sure.
Whatever. I'll take the W. B is correct. Yep. Yeah, but that was easy. D, that's correct.
God damn, I'm scoring points.
C, that's correct. B, that's correct. A, that's correct. C, that's correct. D, that's correct. D, that's correct. B is correct. B is correct.
Okay, so practically the collective mind of a tenth of the entire student body can make a test. Call the news.
Whoa!
Easy, easy.
Here,
Well
yeah.
played, guys.
They say
if we
here
hadn't
double
been able
rotation,
to-
guys. Double rotation. That's 1, and then the main nodes is the second rotation. That's good. This is so that's 2. Okay,
Ooh, I think
this
we
one
had
is wrong.
Yeah.
We said 2 underflows. We end up with this.
Yeah. So the first they count the first transfer as not underflow.
Okay, yeah, they count the first thing as not an underflow. That's fair. I'll take the L for that one. Whatever.
Take the W. Ooh, we're not taking a W.
I feel like you could argue that though with someone.
Which of the following?
Hey, they're both correct.
No, they're not. They are incorrect.
But no, wait. Why are they both?
I have
think
no idea,
because
Jelle.
I think that
Because
it's incorrect.
of the slides.
I think that because of the slides, this is still like they would accept this answer in an exam.
Yeah. Okay. Fair. Hey, B is 14 because we wrote it out. Then now the open
And
questions.
here, let's be fucking strict to ourselves.
You're gonna get fucked.
So this is the sum of all v deg v. That is still or
what?
I guess the sum of all v deg v, if it is a directional tree, isn't necessarily, but is it directional though? Because an edge list isn't directional, so it had the sum accounts also for like.
Does it say that we can simplify it more? No.
Wait, where are we getting C1n from here? And why don't we have it in our?
All the calls to G dot vertices.
Yeah, so you go past all the.
Oh,
Wait,
so that's
all the
not constant time. So we took it as constant time, but it's not.
Yeah, we thought it was a lazy iterator, but we create a new iterable, a new collection. So that's why it's n times probably.
I
N
see.
time.
All right, we would get like maybe 1 point here or something.
Out of 5.
Yeah.
I wonder.
I don't think so.
I wonder why C3 doesn't why it doesn't sum. Because the sum of all degrees is 2m.
We do that in the next part. Look at the next part. We do that.
Yeah. Okay.
Huh.
It can be simplified.
Okay, it can be simplified. Yeah. Yeah. Okay. So the sum of all degrees v. Yeah, we call it n deg v. They just call it the sum of.
Yeah, but the problem is it is smaller than it. I thought it would be the same.
Okay, but not
No,
everything is connected.
It says so. It is. The sum of deck V equals to M.
Oh, okay.
So I don't know
Because it
why
doesn't
they're
have
using
parallel
the.
edges or left loops.
I'm not sure why they're saying smaller equal because it's just the same.
Yeah, but we would get like. I think we would get 2 points then.
Yeah, for the second one definitely. For the first one we might also get 2 or 3.
Okay, I'll
We
count
will
it.
get 3 for the second one because we only had one mistake out of the 4 terms.
For the second one, we only get 2 points.
Yeah, but
No, for the first one, I think we should get like 3 or 4 because we just had one term that was incorrect.
I think
So
you only
correct.
get 5 if everything is correct.
Yeah, so let's see, we missed out on. So we had.
C1.
So the C0 here, their C0 is our C2, that's correct.
This
we
one,
only
the
had.
C3 one is incorrect.
We didn't have this one, and yeah, we just didn't have that one.
So 3.
I'll call it 3. We would need to be conservative because they might fuck it over.
But did we figure out yet why they say a smaller than or
That's
equals sign?
Yes.
Not really, but they say it's equal, so.
Yeah, it's strange. Okay.
Okay, if a graph G was implemented, blah blah blah. Oh yeah, okay, but that's just what we had.
Oh, we had O.
Oh wait, we had
of
big
M.
O of M.
This is O of N plus N. What the fuck?
Well, that's
C2 and
because
M.
for the same reason we forgot the
Yeah.
this term.
Oh yeah, okay, that makes sense. Oh yeah.
So I'm not sure what we would get for this though. We have the wrong complexity, but we did add we did say this thing correctly, so I'm gonna give it 1 point.
Yeah, sure. Because
Then for
this is
24.
this is definitely the questions where they are the most strict ever.
Yeah.
Especially now they're gonna be even more strict because open book and you have like.
Yeah, like this exam was for us when we had closed book.
Yeah, which I'm surprised about, honestly. The questions were like, I see how the pass rates are that low if you have closed book.
Yeah, like I could not have done this with closed book, and even with open book, it's kind of hard. Okay, so we have this.
It's incorrect for us.
And
It's
no wait.
2S.
Yeah, we have like we said it 2 here.
Yeah.
Account for the recursive calls.
Doesn't make any sense. How does it account for recursive call when there are 2 recursive call and it's only taking 1 in consider?
Exactly.
Is their answer the same?
No, it will completely change because 2 will change the entire thing.
Yeah. That is so weird.
I think they are wrong here because we're having 2 recursive call and they're not considering both the recursive. They're only considering one of them.
Doesn't it only make sense to have 2 if we're talking about time complexity? But since we're talking about space complexity, we don't have the 2 times as
Yeah, because once the first one is finished, you start working on the second one.
And you reuse that space. Yeah, I think that's it.
Motherfucker. But does that mean
So everybody needs to make a note of that right now.
Yeah.
Because that
Does
will
that mean
fuck
it is
you
never
over.
possible to have a constant here in front of our?
It is if you, I guess, if you run 2 things simultaneously. No, you can't run
No, you can't do that.
simultaneously.
So you cannot do that. Okay, that's good to know.
See, we're
Okay,
learning.
well then you know we probably got at least some points, but like not all of them.
Yeah, we missed the thing that they wanted us to go for. So I'd say 3.
Yeah, let's give us 3 points there.
2.
Okay.
Because we fucked up this, the entire other part is fucked. Like everything else, because
I mean,
everything.
it depends if they call doorrekenfouten.
Yeah, and the entire other part is not what we're grading here. For that thing, all we're grading is the first expression, for which we got 3 out of 5, I would say.
Yeah, I actually think I would give us like 2 points here because we have arrived at the right conclusion given our answer there. Oh, and actually I forgot this one real quick. So,
I think if the TA is nice enough, maybe we'll get 2. Otherwise, it's a solid
yeah.
0.
This one, I think we would actually still get a big part of the
4
points.
or 5 maybe.
Yeah, I'm gonna say 4. And then for D, yeah, here they just literally this is my function.
Yes, like line for line.
Yeah. So,
yeah, great.
Yeah, so that is how many points? 2 points. Consider the following tree. Yeah, well, that's what we had, right? Yep.
There's 2 trees. Yep.
So this is correct for 1 point. Okay, 1 point. This is correct for 2 points. Oh wait, that's still 1 point as well. Yep. Well, I mean, I say it's a multi-way search tree, not a binary search tree, so that's actually wrong.
Well, an AVL is a well, an AVL is a way to display a binary search tree.
Is
yeah,
it though?
it can be multi-source, no?
Yeah, because this isn't. Oh wait, no. AVL
Because
and
it's all about the
2,4
high
tree.
property, not if it's just one thing.
Yeah, no, this is a 2,4 tree, not an AVL tree. I was thinking of.
Yeah.
So
Okay, so we got one of
are,
it. So we got the balance condition, but not the first one. So that's 1 point.
I'm gonna say 1 point. And
we also got the last one wrong then.
Well, I mean, we had no.
Actually, we have this one correct, but for the wrong reason, which is fucking
No,
nice.
no, it's good. A counterexample is the answer of question 25a. So that's full point.
Yeah, no, exactly. Like I said, we got it right, but for the wrong reason, because we were comparing it to a 2-4 tree.
No,
but it doesn't matter.
We were using AVL tree because we were using the definition that we looked up here. I just thought multi-way search trees had that as well, but they don't. Okay, so let's have a look at what we would have gotten. So it's 5 times score divided by 50, score divided by 30. So final score open 2 plus 1 plus 1 plus 1 plus 2 plus 2 plus 2 plus 1. Let's see, 2 plus 1. So that is this 2, this 1. Then we get 2, 3, and that's the last one. Plus 2 plus 3. Then we do all of this and we divide it by 30, and then we do that times 5, divided by 30 times 5. And that's 2,83333. And then we just add those together, right? Yeah.
Yeah, 50-50.
And then we have final score closed. That's the amount of points we had correct, divided by 22. Well, that's all of them except for 1, so that's 21. Divided by 22 times 5 equals... I wonder if we will pass, guys.
We'll pass with that.
Obviously. Okay, so then final score is a 2.83 plus 4.77 equals to, it's like 7.6. So
I expected higher.
I expected a lot higher.
Much higher.
What we got?
A 7.6.
Holy shit.
Holy shit, and this is like a closed book.
Holy fuck.
Yeah, no, it said no. Oh.
Well, you have it too.
Right?
Yeah.
Wait, hold on. Can you go to the left? No other materials, yeah.
Yeah, so this should have been closed book. Jesus fuck.
Well, I mean, a handwritten double-sided A4 cheat sheet would have in it, like if you just sketch over the all the tables, like the ON things and tables and shit, then you would already have 90% of the first things.
Yeah.
Like of the closed or the open or multiple choice questions.
Can we go to the question about the 2-4 tree? Question 20.
Question 20. That's the one we got wrong, right? Yeah.
Yeah. I don't get how.
Okay, so what they say is after a node gets removed, like they add this one. We saw that as a transfer, while they didn't.
Okay.
Yeah.
Oh, we also considered transfer, but we also considered it as an underflow.
Yeah.
So there is only one underflow. But there are like there are two transfers. So like the one transfer is to like the 31, and the other one would maybe the 80 to 91.
we thought this was a transfer and this was a transfer, but they just thought, okay, this is the start state, and then this is a transfer.
A different thing, underflow. We thought there were two underflows.
Yeah.
There's only one underflow that happens in the second part.
Yeah, but we thought like before we got to this state, this thing will be 30, this thing will be empty, so then there will be an underflow.
Yeah, but that's just a transfer. It's not an underflow.
Yeah, but it's also not a transfer.
It says that after performing a transfer, we end up with this.
Yeah,
After
but so this one is a transfer, but this one isn't.
Yeah. Fair
So there's only one transfer, one underflow. However, we thought that this thing, here, the node will be replaced by the maximum in order, whatever. So, yeah, we thought it was 2, but it was 1. So the only question we had wrong was because of a misunderstanding.
That's dumb.
All right, so that is pretty scary. The fact that we only got a 7. Though I must admit that is mostly because of like we didn't understand, or at least I didn't understand space complexity well enough.
All of us, we were all with that.
Yeah, that was all of us.
I mean, I was mostly reading, browsing rather than I don't think all of us are paying full 100% attention. But yeah, I must admit.
Yeah.
And
I
got
forgot that
I got a 4.7 on my midterms because I had like an 8 for the open or for the closed question parts, and I had practically a 6 for the closed question parts, but I missed one thing in the complexity functions, and complexity functions are like. Complexity analysis is really where they fuck you up on, and it's almost the only thing they ask in open questions. So you should really, like I said at the start, just do one by yourself and look how they grade it and see if you've got it correct, because they will fuck you on it, like actually.
Yeah. That was rough. But
yep.
Now we know. What mistakes
you
you made?
Fucking we own by yourself. You would only have to have like 60-70% of what we got correct.
Yeah, but that's not a lot of room.
No. I'm like out of all exams, this is the one I'm sweating most.
Yeah.
But it is definitely doable. It's just not doable with higher than a 7.
Yeah, I got like a 9, and I got a 9 for everything in the first subject. For the first quarter, I am really hoping for like a 6 for this. That's all I ask.
Same.
I'm hoping to pass. If I pass, I'm gonna give like I don't know. There'll be a party, I guess. People party because legal.
Minimum we need is it 5.5 or 5.8?
Yeah, it's I think we need a 5.75, so it's 5.8.
Alright, well I know what I need then. I know what I got.
Hopefully gonna be getting those points from the implementation. Wait, I swear we haven't even gotten our grades back yet
for what?
The midterms.
For which one?
For ADS.
ADS, if you go to the midterms, like on WebLab.
Oh, is it on WebLab?
I'm not sure if it was. I remember seeing, anyways, the like the breakdown of my points.
Oh, yeah, I just saw. Okay.
Yeah.
Yeah. It is very useful. It's more useful to do that than to look at this. It's better to know what you don't know than to be here listening to people who say, yeah, it's this and that.
Yeah. However, that is the end of the recording. I'm going to go downstairs. Everybody have a good one. Good luck on your test. You got this, King. And we'll see you in the next video.